March 1959. Vol.8, Number 3. Producing Magnetic Memory Cores. Make your tabulating department a service department. A survey of British digital computers. The most serious of facts. Power when wielded by abnormal energy is the most serious of facts, wrote Henry Adams in The Dynamo and the Virgin. One serious fact is the birth of the handful of power. Above, the early form of a transistor-regulated power supply. Developed by Tech/Ops, now in production, in sophisticated forms by Tech/Ops subsidiary, Power Sources, Incorporated. Best suited for arduous requirements in applications demand reliability under extreme operating conditions which force rejection of conventional power supply circuitry, such as guided missiles and other military space needs. This hand full of power is also presently being used in television stations, as in a host of other applications. And it is another typical example of Tech/Ops product capability and broad scientific research and development for business, industry, and government. Technical Operations, Incorporated. Central Research Laboratories / Burlington, Massachusetts. Washington, D.C. Monterey, California. Fort Monroe, Virginia. Personnel requirements. At Fort Monroe, Virginia, or Burlington, Massachusetts, operations ANA. LYSTS experienced in industrial or military operations research, systems analysis, weapons systems evaluation, computer techniques, or related fields, training. Should be in mathematics or physical sciences, preferably on graduate level. At Washington, D.C., programmers with substantial experience in the development of large digital computer programs. Background should include experience with design and application of assembly programs, compilers, and advanced programming concepts. At Monterey, California, communications engineer or physicist thoroughly familiar with the principles of radio transmission and communications net work analysis. Address: Robert L. Kohler. Computers and Automation for March, 1909. Computers and Automation. Data Processing Cybernetics Robots. Volume 8. Number March 3, 1959. Established September 1951. EDMUNDC Berkeley Editor. H. Jefferson Mills, Jr. Assistant Editor. Neil D. MacDonald Assistant Editor. Service and Sales Director. Milton L.K. 535 Fifth Avenue. Murray Hill 2-4194. New York 17, NY. Contributing Editors: Andrew D. Booth, Ned Chapin, John W. Carr, 3. Alston S. Householder. Advisory Committee: Morton M. Estrahan, Howard T. Engstrom, George E. Forsyth, Richard W. Hamming. Alston S. Householder: Herbert F. Mitchell, Jr. Samuel B. Williams. Advertising Representatives: Middle Atlantic States Milton L.K. 535 Fifth Avenue. New Cork 17, NY. Murray Hill 2-4194. San Francisco 5. 605 Market Street. Los Angeles 5. 439 Southwestern Avenue. A.S. Babcock. Yukon 2-3954. W.F. Green. Dunkirk 7 to 8135. Elsewhere the publisher. Berkeley Enterprises Incorporated. 815 Washington Street, Newtonville 60, Mass. Decatur 2 to 5453 or 2 to 3928. Computers and Automation is published monthly. At 815 Washington Street, Newtonville 60, Massachusetts, by Berkeley Enterprises Incorporated. Printed in USA. Subscription rates, United States, $5.50 for 1 year, $10.50 for 2 years, Canada, $6 for 1 year, $11.50. For 2 years, foreign, $6.50 for 1 year, $12.50 for 2 years. Address all editorial and subscription mail to Berkeley Enterprises Incorporated, 815 Washington Street, Newtonville 60, Mass. Entered as second-class métier at the Post Office at Boston, Mass. Postmaster, please send all forms 3579 to Berkeley Enterprises Incorporated, 815 Washington, St., Newtonville 60, Mass. Copyright, 1959, by Berkeley Enterprises Incorporated. Change of address. If your address changes, please send us both your new address and your old address, as it appears on the magazine address imprint, and allow 3 weeks for the change to be made. 4. Novel applications of computers. Computer aids research for better beef. C.J. Brown. Crewless vehicles. Simulation of consumers' decisions. C. Joseph Clausen. Automated capitalism. Edward G. Brander. University student scheduling by Datatron. Neva Sabak. Front cover. 12. 12. 12. 12. 13. An in-circuit transistor tester. Point 1, 6. Articles. Producing high-performance low-cost magnetic memory cores for an expanding digital computer. MOOC 9. C. L. Snyder. Make your tabulating department a service. Department 16. Edmund W. McNamara. Readers and Editors Forum. Reaching out by scientists into other fields. 6. Carmen C. Bassor. Association for C. Computing Machinery Meeting, Sept. 1-3, 1959, Call for Contributed Papers 6. The Art of Getting Published 11. Jordan and Van Deus N. Correction. Intensive Summer Courses. Calendar of Coming Events. Reference information. Computer Talks, 1959 Western Joint Computer Conference. Computer Talks, 1959 Electronic Components Conference. Survey of recent articles. A Survey of British Digital Computers, Part 1. Joseph L. F. de Kerf. New Patents. Who's Who in the Computer Field, Supplement. Index of Notices. Advertising Index. Back copies. Bulk subscriptions. Computer Directory. Manuscripts. Who's Who entry form. 15. 31. 31. 14. 15. 20. 25. 32. 31. 38. 33. 33. 37. 37. 36. Computers and Automation for March, 1959. Comma. Dash. The men who represent ESC in the field are all top-flight technical people in their own right. Each is thoroughly conversant with the very latest developments in the fast-moving delay line field, and each stands ready to apply the combined knowledge of the entire ESC organization to your particular problems. Whether you want advice on a standard delay line application. Components Sales Corporation. 218 East Hartsdale Avenue, Hartsdale, New York. Scarsdale 5 to 1050. New York State, New Jersey except Camden and Moorestown, Westchester County. 44 Brattle Street, Cambridge 38, Massachusetts. University 4 to 1727. New England. Electrodesign. 736 Notre Dame Street West, Montreal, Canada. University 6 to 7367. Canada. K Sales Company. 2600 Grand Avenue, Kansas City 8, Missouri. Baltimore 1 to 3800. 7603 Forsyth, Suite 206. Clayton 5, Missouri. Park Blue 7 to 3414. Kansas, Nebraska, Missouri, Oklahoma. Arkansas, Albuquerque, NM, and the following counties in Illinois: Monroe, Calhoun, Jersey, Madison, and St. Clair. ALLVERA and Association, Inc. 144 to 15 Hillside Avenue, Jamaica 35, New York. Olympia 8 to 1828. New York City, Long Island. In IDEESC, antjamber.t.re / or something special from ESC's Modern Research Laboratory. You can be sure of receiving top engineering talent, prompt delivery, and expert, local service. There's an ESC engineer rep very close to you, wherever you are. Why not discuss your current delay and problem with him now? Magnuson Associates. 3347 West Irving Park Road, Chicago 18, Illinois. Keystone 9 to 7555 Teletype CG 913. Illinois, except Monroe, Calhoun, Jersey. Madison and St. Clair counties, Indiana. Iowa and Wisconsin. 1359 West Maynard Drive, St. Paul 16, Minnesota. Minnesota and Wisconsin. Whiteman and Associates. 4029 Burbank Boulevard, Burbank, California. Victoria 9 to 2435. Harry J. White Company. 121 Covered Bridge Road, Haddonfield, New Jersey. Hazel 82304. Camden and Moorestown, New Jersey. Eastern Pennsylvania and Delaware. Mr. Richard Trainer. 115 Greenbrier Road, Towson 4, Maryland. Valley 3 to 6184. Maryland, Virginia, as far south as Alexandria and Washington, D.C. Texo Sales Company. 235 SE 14th Street, Grand Prairie, Texas. Dallas, Andrew 2-0866. FT, Worth, Crestview 4 to 4530. Texas. 1436 EI Camino Real, Suite 5. Menlo Park, California. Davenport 6 to 3797. Arizona, California, Nevada and F at 7F. LT. Write today for Cooley T::I: IBQQ. Exceptional employment opportunities for engineers experienced in computer components. Excellent profit share NF plan. E0RP0 Ration. 534, Bergen Boulevard, Palisades Park, New Jersey. Distributed constant delay lines, lumped constant delay lines, variable delay networks, continuously variable delay lines, push-behind decade delay lines, shift registers, pulse transformers, medium and low power transformers, filters of all types, pulse forming networks, miniature plug-in encapsulated circuit assemblies. See you at the IRE show, booth number 2409. Computers and Automation for March, 1959. READERS and Editors Forum. Front cover, an in-circuit transistor tester. The front cover shows a testing apparatus which is able to test transistors mounted and connected in their circuits. This is believed to be the first transistor tester able to check the performance of transistors while they are connected in their circuits and without turning power on in the equipment. The tester is now being produced by Philco Corp., Philadelphia. A contract to build more than 900 of these transistor testers has been awarded to Philco by the U.S. Navy Bureau of Ships. This tester is able to distinguish between normal input and output signals generated by the transistor being checked, and spurious input and output signals arising from sneak paths provided by the circuits surrounding the transistor being checked. To nullify the effects of the external circuits, low impedance methods are used in the tester. Association for Computing Machinery. Meeting, Sept 1-3, 1959. Call for contributed papers. The next annual meeting of the Association for Computing Machinery will be held at Massachusetts LNST of Technology, Cambridge, Massachusetts, Tuesday, September 1 to Thursday, September 3, 1959. Contributed papers concerned with all phases of an analog and digital computers and computation are invited. Each person wishing to have a paper considered for the contributed program is requested to submit to the program committee by May 4, 1959, 4 copies of a 100-word abstract, and 4 copies of a summary of the paper. The amount of time which can be allotted to each contributed paper is limited to 15 minutes, followed by 5 minutes for discussion. The abstract should be suitable for inclusion in the printed program of the meeting. The summary should be of sufficient length to permit evaluation of the paper by the program committee, but less than 4 typewritten pages is suggested. 1 copy of the summary should be typed in black ink on white paper to permit photographic reproduction for inclusion in the preprints. Preprints will be distributed to all registrants, and offered for sale by the association for 3 months after the meeting. Authors who do not wish their summaries to appear in the preprints should say so. Abstracts and summaries should be sent to J. H. Wegstein, Chairman, ACM Program Committee, National Bureau of Standards, Washington 25, D.C. Papers for the program will be selected by the program committee after May 4, 1959. It will not be possible to consider those papers whose summaries are not in quadruplicate, nor those papers which arrive after the deadline. 6. Reaching out by scientists into other fields. I. From Carmen C. Basur, Cabazon, California. To the editor. Your magazine has raised the question of the social and moral responsibilities of scientists in regard to the effect of their inventions upon society, whether the effect Be good or bad? To me, this is a timely question. Perhaps your editors are among the first to realize its increasing importance, for I believe that the first-rate scientists of this country are already assuming social responsibility in regard to those effects of their work that extend into international affairs. I see that, in the scientific world we now live in, the implements of war that have been developed are capable of destroying the whole of mankind, and that any scientist, viewing his own work, cannot escape some responsibility, in his own mind, to see that this does not happen. I cannot accept such a point of view as that expressed by one editor, in your poll of technical magazines, who states, "We do believe that any scientific development can be used in a good or bad manner, and it follows from this that the scientist's responsibility in evaluating this is not so much greater than the average citizen's." Such questions are philosophical and should be aired by philosophers, but finally determined by the citizenry. For me this view means that all we scientists can do is duck our heads and take what comes, and nothing can be done about it. But of Kotlin this is not true. The leading scientists of our country, whose study of science has greatly broadened their minds, have mastered their own field of endeavor and are then able to look about them, understand other fields, and relate their work with other aspects of society. The capacity of an able scientist to relate his work to other fields has been illustrated in the recent past, as with the quantum theory, when the theoretical developments of science have led into philosophical concepts that traditional philosophy was unable to cope with. To meet this situation, the scientist had to take over the job of philosopher and had to provide a philosophic interpretation that would allow him to proceed. This caused strong objections from some professional philosophers who felt that the scientist was incapable of entering another field of knowledge with any success. Of course, the real obstacle probably was the fact that philosophers were not able to keep abreast of the advances of science and were not able to develop the. Please turn to page 30. Computers and Automation for March, 1959. 1190. To senior computer programmers interested in research and development on advanced programming techniques. Those interested in performing research and development on advanced programming techniques will find full scope for their ability at System Development Corporation in Santa Monica, California. SDC's projects are concerned primarily with developing large-scale, computer-centered systems in a number of fields. The application of advanced digital computer techniques is particularly important in these systems. As these systems are computer-based, programming is an essential function at SDC. Programming is a service activity at SDC. A few positions are open for senior computer programmers. The positions call for strong experience and ability in programming and keen interest in methodological and program techniques 0/retrieval logical design 0/computers from a programmer's point of view, pattern recognition and machine learning language translation, both natural and computer-oriented languages. Those who desire additional more information are invited to contact William Kiefer at System Development Corporation, 2406 Colorado Avenue, Santa Monica, California. System Development Corporation, Santa Monica, California. Computers and Automation for March, 1959. 7. Speed routine calculations increase creative time. With this powerful electronic computer, Royal Precision LGP30. Large capacity, easily programmed and operated, mobile, low in cost. Compact, simple to use, Royal Precision LGP30 will today bring high-speed computation right to your desk. Thus relieve you of the tedium of standard hand calculations, increase available time for truly CRE-ative work, help you simulate optimum designs in a matter of minutes, and at the lowest cost ever for a complete computer system. Unusual capacity. Operating from a standard wall outlet. Performing an almost unlimited range of calculations. LGP30 gives you the flexibility of stored program operation combined with speed, memory, 4096 words, and capacity equal to computers many times its size and cost. Completely mobile, LGP30 is easily wheeled from room to room, building to building. 8. Simple to operate and program. LGP30 controls have been so thoroughly simplified that it may be operated with only minimum computer experience. Direct printout of answers, no deciphering required. Programming is easily learned even by non-technical personnel. Library of subroutines, plus programs for a wide variety of applications, is available. Wide range of applications. In addition to general design and system optimization, LGP30 is currently being used for the refinement of estimates, computation of design parameters, specification of new product properties and capabilities, calculation of such data as reactance, load saturation curves, time constants, harmonics, torque speed, and V-curves. Exceptional value, complete service. Smallest initial investment ever for a complete computer system is combined with low operating and maintenance costs. Service facilities coast to coast. For further information and specifications, write Royal McBee Corporation, Data Processing Division, Port Chester, NY. Royal McBee, world's largest manufacturer of typewriters and makers of data processing equipment, computers and automation for March 1959. Producing high-performance low-cost magnetic memory cores for an expanding digital computer market. C. L. Snyder, Vice President, General Ceramics Corp. Kismet, NJ. Electronic digital computers were first reduced to practice in the middle 1940s. Since that time, as their speed and reliability have increased, these computers are being more and more widely used to solve industrial and military engineering problems, handle production controls and speed, and simplify office procedures. One of the most important components in the computer system is the memory, since nearly every operation of the computer requires access to it. Heart of the internal memory in most large modern computers is the ferrite magnetic memory core. This is the most reliable means yet developed of providing high-speed random access memories, which permit information to be obtained in any sequence desired. When these tiny magnetic cores first became available in small volume, their cost, although competitive with that of other available systems, was high, nearly SOC apiece. This presented what seemed to be a problem to the growth of the computer industry, but within the past 5 years General Ceramics, through plant investment and research, has reduced the cost to about 3C each. improved the yield of quality cores from 30% to 98%, and increased the production from 1,000 to 250,000 daily. History. The first practical memory device for electronic digital computers was the Mercury delay line, and some early digital computers were built using this storage method. In a few years these delay lines were replaced by cathode ray electrostatic storage tubes which operated more rapidly and permitted an increase in the size of the memory. But storage tubes are expensive to install and maintain, and the memory was a volatile one and subject to errors every few hours. It soon was recognized that it was possible using magnetic devices to construct a memory storage system that would make no errors, be permanent in character, have a large capacity for memory bits in a relatively small space, and be much less expensive. A few memories were made using metallic tape wound cores which demonstrated all these advantages with the exception of low cost. In the meantime experiments were being conducted using ferrites as memory devices. These are magnetic ceramic materials which have many of the characteristics of metallic magnetic materials, but have an internal resistance which is enormously greater. Ferrites reduce eddy currents to a negligible factor, and thus have their ability to handle higher frequencies. This in turn made them operable on far smaller electrical impulses. Experiments further showed that ferrites could be made which have a response time 2 to 4 times faster than the best of metallic tapes in coincident current circuits. Computers AJJD Automation for Mark I, 1959. In the late 1940s Dr. Ernst Albert Schenberg, Gen. Ceramics Director of Research, and pioneer in the development of ferrite materials, developed a unique ferrite material which exhibited a rectangular hysteresis loop pattern. This material provided a practical solution to the memory storage problem. Essentially the same materials are being used in cores today. The rectangular hysteresis loop ferrite core is magnetized by a small amount of driving energy which exceeds a certain threshold value, the core remaining magnetized when the energy is turned off. When an equal amount of reverse energy is applied, however, the magnetic polarity is reversed. The core remains in either of two states of stable magnetization unaffected by time or external influence other than the specifically applied driving force. Each core stores a single bit of information which can be correlated with the numbers 1 or 0, which are the basis of the binary system of numbers used in digital computers. Through a system of circuits this information is broken down into arithmetic operations of addition and subtraction to provide the solution of the problem being solved. In December 1949, Dr. Albert Schoenberg published his findings. They came to the attention of William Pappian of Massachusetts Institute of Technology's Lincoln Laboratories, who was actively involved in the development of a reliable large high-speed memory system. As a result, a joint development program evolved, in which General Ceramics and Lincoln Laboratories co-operated closely. Within a year ferrite cores were commercially available for use in random access memory devices. The first of these cores were used to replace the electrostatic storage tube memory in the MIT Whirlwind digital computer. The new memory equipped with the ferrite cores, while of the same size as the earlier system, had a speed 3 times as fast, occupied only 1/4 the space and reduced the air con. The T1ing load by 4 tons. A further result was reduction of memory errors from 2 to 3 each 24 hours to only 1 in the first 6 months of use. Production. Ferrite cores, the latest of which have a response time of 1 microsecond, are produced in the shape of rings, so that all of the flux generated by the driving circuit can be coupled to th largest possible area of magnetic material. The rings are extremely small. Of the two sizes now available, one has an outside diameter of 0.080 and an inside diameter of 0.050, while the other has an df kdrr-t 0.059 phi j li oxide 95 cl phi tealer than 0.5 microns, to which are added 4 to provide the desired magnetic properties. Binders and lubricants also are added to assist in subsequent forming operations. Protracted wet ball milling yields a mixture that is very fine and homogeneous. The ferrite material is dried, and from the product, the cores are pressed and fired. Since firing is one of the major factors affecting performance, an entirely new kill technology, based on exact control of temperatures, rates of heating and cooling, and special atmospheres during heating up, soaking and cooling, has been developed for ferrite manufacture. General Ceramics produces a broad line of ferrite products other than the rectangular hysteresis loop mat reals, and this broad development and manufacturing effort has led to materials and production control and economies that have been very advantageous in the production of TE memory cores. These other ferrites have different chemical compositions, are subjected to different physical and thermal treatments, and have magnetic properties which are different from those of the MEM Ori cores. They are designed to perform specific magnetic functions, many of which were formerly unattainable either in kind or degree. For example, one small ferrite antenna rod gathers feeble radio signals so effectively that it has rendered portable wire wound antennae obsolete, while at the same time making possible miniature portable radios. Other types of ferrites have important applications: magnetic cores for recording heads, saturable reactors, deflection yokes, permeability tuners, permanent magnets, and special transformers. Some are magnetic materials specifically designed to yield high efficiencies within different frequency bands. 2 unusual qualities may be noted. The first is that these magnets are electrical semiconductors, with the result that eddy current losses can be reduced to very low levels. The second is that by altering the composition, a wide range of magnetic permeability and coercive force can be designed into the magnets. For example, a very high coercive force, which is a measure of the resistance to demagnetization, has been developed in certain barium ferrites, with the result that permanent magnets resist demagnetization to a greater degree than any other magnetic material. Testing and handling. No equipment existed to test finished memory cores when production began 5 years ago. The evolution of test equipment has run parallel to the development of the cores themselves. Some testers are now commercially available, but the design, development, and modification of testing equipment by General Ceramics has become an integral part of the manufacturing operation. This equipment includes devices for measurement of permeability and coercive force, current calibrators, voltage calibrators, low-level sense amplifiers, current sources, and high-speed core handlers. The two primary areas of consideration in the design of this equipment are current sources and core handling. The current source testing equipment simulates the smallest possible electrical information pulse while in Figure 1, an automatic core handler. To computers and automation F9F March, 1959. Figure 2, an automatic core tester. Introducing a high degree of disturbing outside influence into the wire system, this determines the core's stability level. But this has never presented a major problem. Most of the difficulty in making test equipment has centered around handling the very small cores, which are about the size of a pinhead. Originally the operation was entirely manual, and a wire to contain the test current was placed through each core by hand. Only 1,000 to 1,500 cores could be tested daily by this method. An automatic core handler then was developed which handled 6,000 to 8,000 cores daily but still required the operator to determine the rejects. The next step was the development of a fully automatic tester to eliminate human decision. The first of these handled 1 core per second or 25,000 per 8-hour day. Fully automatic handling and test equipment has since been upgraded twice. In the first of these improvements, core handling speed was increased to 4 per second. And the equipment now in use handles 10 per second or 250,000 cores per 8-hour day, as well as measuring additional parameters of the core. As core testing and handling speed have increased, production improvements have kept pace and the core reject rate has dropped sharply. Core performance, present and future. Present-day cores are used in large high-speed digital computers and such other equipment as buffer MEM, ORIs, digital voltmeters, industrial programmers, redundancy devices, even jukeboxes. They are uniform in quality and performance, are stable indefinitely, economical to use, inexpensive to measure and calibrate, and fast in response time. Development work, however, is being actively pursued and higher performance standards are continually being attained. Computers ALT Automation for March, 1959. Production has begun on cores of 0.050 inches about side diameter in contrast to the 0.080 inches of the earlier cores. This change permits many more bits of information to be stored per cubic foot. The smaller cores also allow the use of transistor drives with greater reliability and simpler circuitry. Presently available materials with switching times of about 1 microsecond soon will be complemented by new materials having twice the switching speed. Thus, the struggle continues to improve and make perfect. The art of getting published. From Jordan and Van Dusen. Laguna Beach, California. We are often asked if we guarantee the publication of technical articles that we may be commissioned to write. Our answer: there is no inside track to getting an article published in the trade press. If the article is well written, informative, and newsworthy, it will be printed. If it does not meet this test, all the personal contacts and advertising schedules in the world will not make up for the lack. Editors are constantly looking for good technical articles. Editors judge an article by just one measure: its value to the reader. The reader must get something out of the article or it will not be printed. The more technical the subject, the more difficult and important this becomes. Engineers cannot be convinced by unsupported claims or adjectives. They want to be educated but with facts. They can tell, like the editor, when a technical discussion is only an advertisement in editorial dress. 2 from the editor. Here. If novel applications of computers. Computer aids research. For better beef. C.J. Brown. University of Arkansas. Fayetteville, Ark. Development of much more productive and economical types of beef cattle is being aimed for by use of an electronic computer, installed at the Department of Animal Industry and Veterinary Science at the University of Arkansas. The computer is a G15 general purpose digital computer produced by the computer division of Bendix Aviation Corporation. The computer will be programmed to determine and interpret trends and correlations in the qualities of beef, cattle and allied livestock. Statistics concerning breeding, efficiency of production, mothering ability of cows, weight of animals, body measurements, and various feeding and digestive factors in different breeding groups, etc., will be processed. Statistical data projected over generations of cattle eventually should take the guesswork out of breeding. Simulation of consumers' decisions. See Joseph Clausen. Facts Consolidated. Chicago, 111. Based on a talk before the American Marketing Association. Chicago, Ill., December 30, 1958. Computers are used in the simulation of the probable flight of an intercontinental ballistic missile or a space rocket. In the same way, it may soon be possible to give trial flights to promotional programs on electronic computers. They may make it possible to forecast with greater accuracy the behavior of consumers in response to marketing programs which are under consideration. I believe there are many indications that the decision and action process of consumers will soon be simulated, or at least reduced to a systematic set of mathematical functions which can be programmed onto an electronic computer. In this way, we will be thinking about a representative sample of consumers in a way similar to the way they think for themselves. Crewless vehicles. Charles 1. Patterson, chairman of the Transit Authority of the City of New York, which operates the city subway trains, has reported on a year-long study of crewless trains. Engineers of the authority and 4 electronics companies have explored the feasibility of running subway trains by remote control. The shuttle subway trains between Times Square and Grand Central, about 3 blocks, would be a logical first test. If the 12 system were successful, it could mean the transfer to other work of 90% of the 3,100 motormen and 775% of the 3,500 conductors now employed by the New York City Transit Authority. Michael J. Quill, International President of the Transport Workers Union, and Matthew Ginnan, President of the New York Local, have protested the dangers of tampering with the safety of millions of passengers daily. But they apparently did not discuss the point whether passengers might not be safer with guidance systems that make fewer mistakes than human beings. The Soviet Union has reported a recent test run of an automated train between Kuntsevo, near Moscow, and Yusovo, a distance of about 300 miles. In this test, an automatic control system replaced the train engineer, made computations solving problems in connection with the train's move merits, and interpreted coded information on the grade of the tracks, the distances between stations, and other such data. The elevators in a number of New York's new office buildings with 20 to 30 floors have no human attendants. The automatic elevators appear to operate more safely and efficiently than those having human operators. There are no signs in those buildings, however, saying how the displaced elevator men are now earning their living. Automated Capitalism. Edward G. Brander. Brander and Brander. Wayne, Mitch. Some time ago, a number of small groups of people got together to study the stock market, needing edu cation in the way that investments in the stocks may be wisely made and to learn how the stock market operates. The groups joined together in a cooperative effort, and established a national association of investment clubs. These clubs are composed of 10 to 15 people, who need guidance in their education, and learn by actually investing in stock of their choice. But what stock should they buy? The NARC published a 4-page NARC Stock SE lection guide, which formulates the principles and policies of the investments of the clubs. These principles require plotting sales and earnings records for 10 years past, and their projections for 5 years in the future. The price-earnings ratio, the dividend payout, and the return on invested capital are also averaged for 5 to 10 years. The current investment yield is also computed. A prediction is made by a formula for the possible high and low prices 5 years from now. From this information, zones for buying, holding, and selling are established and compared with the market price. Doing this analysis for a stock manually required 1y2 computers and automation for March 1959 to 2 hours of work, and some pulling of teeth and tearing of hair. But one of our staff members who was in our club programmed this process for our Royal McBee LGP 30 computer. Zoom, 10 minutes analysis time. So we now enjoy 6 to 8 analyses per month to look at and consider each month. The computer program also permits speedy updating of the reports of the stocks that we have in our portfolio, as well as 40 other stocks that we have examined but not purchased. Through cooperation, at least 7 other clubs from Poughkeepsie to Phoenix are also using this investment analysis computer program. The printed out report is a delight to behold, with its alphanumeric, precise tabulation and color shifts. Viva la capitalism, and computers. University student scheduling. By Datatron. Neva Sabak. Purdue University. Lafayette, IND. Purdue University students of the past and even up to a few years ago remember the seemingly endless hours of waiting in line to be registered, first at the registrar's office, then at the armory, and later in Quonset huts. What a bother, they grumbled, to have to walk into registration headquarters, wait in line while the guy in front argued with the registration official. And then when your turn finally came, you found out that the class you had to be in, it was your last semester and it was a required course, was closed. This meant starting all over, again consulting with your advisor, again trekking to registration headquarters. Again. But that's all over now. At least the long lines are getting to be a thing of the past. Through the efforts of Mr. James F. Blakesley, Administrative Coordinator of Schedules and Space, and other staff members devoted to helping Purdue operate efficiently, Purdue's digital computer, the Datatron, has been adapted to the SCHED ULing process. Purdue is the first university, so far as we know, to use this practical and satisfactory way to schedule students electronically. Although the machine was bought from Electrodata Division of Burr Ruffs Corp for research in the statistical laboratory, it was found to be of great use in student registration and scheduling. The Datatron electronic digital computer memorizes in about 5 minutes the 1,400 courses and 4,000 DV Zions that may be selected by students. The machine also knows the course identification, the maximum size of each class, and the meeting time of each class. As students are scheduled and divisions of courses become filled, a method is available for opening additional divisions. Here's how a student is scheduled electronically. He goes to his counselor and together they list the courses he is to take in the next semester. This information is translated into Datatron language through pre-punched cards and fed into the machine. In processing the SCHED UL, the computer schedules first those courses with only one division, because this division has no alternate time schedule, and then continues to schedule courses by a predetermined priority. The machine keeps track of available spaces and equalizes the number of students. Computers and Automation for March, 1959. Assigned to particular sections of a course by attempting to schedule the section with the most remaining spaces. First, if a student plans to work, he signs up with his advisor for a period of free time. If no conflict develops, this free time will be scheduled along with the other courses by the Datatron. In a matter of seconds, in many cases 35 or 40, out of the computer comes the student's schedule of classes, punched on cards. Tabulating equipment is used to produce the student's schedule in readable form. Advantages of the Datatron are numerous. First, there is the speed of selecting sections of courses to meet the student's requests, free from conflicting hours. Second, course section enrollments are equalized. Third, the last student through the computer has nearly the same opportunity to be enrolled in the courses of his choice as the first student. Fourth, the instructors have classes of a more uniform size. An additional benefit of equalized enrollments is found in more effective use of instructional rooms, that is, fewer rooms are needed. Since the classes are spread among many rooms at various times instead of using a large number of rooms at a peak hour. Finally, the staff members previously busy with registration details are freed for counseling and instruction. The machine is no more infallible, of course, than the information put into it by human beings. But, once it begins its electronic scheduling, it does a job no human being can possibly do in 5 seconds or per APS 20-minute use. It is a certainty that no human can make such an even distribution of classes as the Datatron does in the same time limit. Work on the idea of electronically scheduling students began in 1955. After much probing and testing, the first group of students was registered December 11, 1957, in order to sample a diversified group of students. Agriculture and engineering students were chosen. 209 freshmen AGS were registered successfully by the Datatron. The next day nearly 1,600 freshman engineers were scheduled by the same procedure. A maximum time of 2 minutes and a minimum of 5 seconds was used in scheduling each student. This made an average of between 35 to 45 seconds for almost 1,800 students. Since that time more than 20,000 registrations have been processed, with a similar average time for scheduling on the computer. Enrollment is promising to double at Purdue University in the next few years and threatening to triple by 1970, but the Datatron still promises quicker and more practical individual scheduling of students. It will also give them the advantage of better class room atmosphere, free from overcrowded conditions. The student is not turned into a mere number by the Datatron, he receives his own schedule tailored to his individual needs. The university benefits in utilizing its staff to near maximum efficiency in doing the job it was expected to do, and the number of rooms that are needed for instructional purposes are reduced to a minimum. If any reader of this brief report is interested in this application and has access to a high-speed computer, he is invited to contact Mr. James F. Blakesley, President's Office, Schedules and Space, Purdue University, Lafayette, IND, for more information and details of the program. Ming Technique. 13. Computer Talks. 1959 Western Joint Computer Conference, Fairmont Hotel, San Francisco, March 3-5, 1959. New Components and Circuits /CL1 LAS, Aero Neutronic Systems Incorporated. A multi-load transfluxer memory /DG Hamel, W. L. Morgan and R. D. Sidnam, RCA. Design and Analysis of MAD Transfer Circuitry /DR. Benyon and H. D. Crane, Stanford Research Institute. A magnetic matrix memory for semi-permanent information /D. H. Looney, Bell Telephone Laboratories. Card Changeable Non-Destructive Readout Twistor Store. /J. Janik, Jr., J. J. DeBusk and B. H. Simons, Bell Telephone Lab. Square Loop Magnetic Logic Circuit /EP Stabler. General Electric. Information Retrieval and Machine Translation /C. Bourne, Stanford Research Institute. Relative Merits of General Purpose and Special Purpose Computers as used for information retrieval /A. Opler and N. Baird, Computer Usage Co., Inc. A Special Library Index Search Computer /B. Kessel. Computer Control Co., Inc., and A. DeLucia, Rome. Air Development Center. Programmed Interpretation of Text as a Basis for Information Retrieval System /L. Doyle, System Develop. Ment Corp. A Theory of Information Retrieval /C. Walker, Hughes. Aircraft Company. The role of U.S. Air Force research and development in information retrieval and machine translation /RSAM. Sun, Rome Air Development Center. Industry's role in supporting high school science prob. Lem/Dr. Paul Hurd, Associate Professor of EDU. Cation, Stanford University. Information Retrieval and Machine Translation /C. Tuarn, Stanford Research Institute. Computing Educated Guesses /ES Spiegelthal, Gen. Arrow Electric Company. A memory or 314 million bits capacity with fast and direct access, its systems and economic consideration /N Bishop, Time Incorporated, and A. Dumais, Con. Suffortant. Information retrieval on a high-speed computer /A. Barton, V. Schatz and L. Kaplan, General Electric Company. The next 20 years in information retrieval, some. GoLs and Preaction/CN Moors, Zader Company. Computer Communication /HC Martel, California Institute of Technology. Simulation of an information channel on the IBM 704. Computer/E.G. Newman and L. Onip, IBM. 14. A compiler with an analog-oriented input language. Marvin L. Stein, University of Minnesota, and Jack Rose. And Don B. Parker, Convair Astronautics. Automatic design of logical networks /TC Barty. Mass. INST of Technology. The role of digital computers in the dynamic optimization of chemical reactions /R.E. Kalman and R.W. Koepke, Research INST for Advanced Study. Baltimore. Simulation of human problem solving /W.G. Bohr. ICEUS, IBM. Education and methodology for use of computers /G.W. Brown, University of California at Los Angeles. The role of the university in computers, data processing, and related fields /Elfine, consultant, Palo Alto, California. The RCA 501 assembly system /H. Bromberg, T.M. Hurwitz, and K. Kozarski, RCA. A program to draw multilevel flowcharts /LM. Haight, IBM. A compiler capable of learning /R. Arnold, Michigan State University. Achieving reliability in operation control /Elfine. Kotlin, Palo Alto, California. Special Purpose Electronic Data System /MV Crow. Lay, RCA. The Residue Number System /H.L. Garner, University of Michigan. System Evaluation and Instrumentation for Military SPE. Chale Purpose Digital Computer System /A.J. Strass. Mann and L.H. Kirkjian, Hughes Aircraft Co. Automatic Failure Recovery in a Digital Data Processing System /R.H. Doyle, R.A. Meyer and R.P. Peto. Witz, IBM. Learning Concepts and Pattern Analysis /PSUPS. Stanford University. A high-speed data translator for computer simulation of speech and television devices /E.E. David, M. V. Mataluz, and H. S. McDonald, Bell Telephone Lab. Some Experiments in Machine Learning /H. Campaign. American University, Washington, D.C. Some Communication Aspects of Character Sensing SYS. TEM/C.C. Heasley, Jr., Intelligent Machines Research Corp. An Approach to Computers That Perceive, Learn, A&D. Reason/P.H. Green, University of Chicago. Military Applications /H. Silverstein, Department of the Army, Washington, D.C. Computers and Automation for March, 1959. Drafting Digital Computers into Tactical Combat / Captain A. B. Crawford, Jr., Fort Huachuca, Arizona. Data Transmission Equipment Concepts for VL Data / Captain W. F. Luebert, Fort Monmouth, New Jersey. A high-accuracy real-time digital computer /WJ. Milan Kamsky, EBSCO. The Man-Computer Team in Space Ecology I. J. McLeod. Convair, and J. Stroud, Naval Electronics Laboratory. New Machines and Systems /M. Montalbano, Kaiser Steel Corp. The RCA 501 high-speed printers, the story of a product development - C. Eckel and D. Fleckner. RCA. A digital computer for industrial process analysis and control /E. L. Braun, Genesis Corp. The Burroughs 220 High-Speed Printer System /F. Bauer, Electrodata Corp. The Acre Computer, a digital computer for a missile checkout system /RI Tanaka, Lockheed. Aircraft Corp. The IBM 7070 Data Processing System /J Svigals, IBM. Computer Applications in Business Environments /R. R. Crane, Touche, Niven, Bailey and Smart, Detroit. An organizational approach to electronic data processing /G Fleming, Boeing Airplane Co. Developing a long-range plan for corporate methods and the dependence on electronic data processing /N. J. Ream, Lockheed Aircraft Corp. A long-range electronic data processing plan for a national multi-plant manufacturing company /G. Redmond, Chrysler Corp. Dynamic production scheduling of the job shop op. Irration /R.N. Kaplan and V.L. Schatz, General Electric Co. Numerical Analysis /R.D. Levy, University of California, Law. Rents Radiation Lab. Survey of Numerical Analysis /G.E. Forsyth, Stan. Ford University. More Accurate Linear Least Squares /R. Von Hold. University of California. Lawrence Radiation Lab. The Cordic Computer, 1, the Cordic Transcendental Computing Technique /J.E. Voider, Convair, 2. Implementation of coordinate rotation and ether. Trigonometric function algorithms by Cordic /D. R. Clutterham, Convair, 3, decimal binary con. Versions in Cordic /D.H. Daggett, Convair. Monte Carlo techniques applied to statistical mechanics. /W.W. Wood, Los Alamos Scientific Lab. Real-time digital analysis and error compensating techniques /WITO, Minneapolis Honeywell Rego. Later Co. Automatic digital metric structural analysis /B Klein. And Chirico, Convair. Problems of the Future /SULAM, Los Alamos Scientific Lab. Blue Sky Session /LN Ridenauer, Lockheed Aircraft Corp. A new approach to high-speed logic /WD Row. Westinghouse Electric Corp. Experiments in information retrieval /R Cochrane. General Electric Co. Communication across language barriers IWF WIT. More, Department of the Navy, Washington, D.C. Program designed to achieve maximum machine utilization. Computers and Automation for March, 1959. Shin in a real-time computing system /AF Rosine. Sylvania. Pattern and character recognition systems, picture processing by a net of neuron-like elements /LA. Kaminsky, Bell Telephone Lab. Philosophy and Responsibility of Computers in Society. /R.W. Tyler, Center for Advanced Study in the Behavioral Sciences, Stanford University. Social Responsibility of Engineers /F. Wood, IBM. Emergency Simulation of the President of the United States /L. Sutro, Datamatic. Can computers help solve society's problems /J. Rothstein, Edgerton, Germshausen and Greer Incorporated. Measurement of Social Change /R.L. Meyer, University of Michigan. Analog Simulation /J.E. Sherman, Lockheed Aircraft. Coral. Simulation of sampled data systems using analog to digital converters /MSU made, Space Technology Lab. Thomson Ramo Wooldridge Corp. A transistorized analog memory for functions of 2 variables /PC Scherertz, and L.E. Stefan, Convair. A time-sharing analog computer /JV Rihing, Jr. Westinghouse Electric Corporation. Computers, the answer to real-time flight analysis. /G Hinsa, Chief, Flight Simulation Lab, White Sands Missile Range. Symbolic Language Translation /EC Glusing, REM. Ington Rand. New Horizons in Computer Technology /H Aiken. Harvard University. New Applications of Computer Technology /HD. Husky, University of California. A generalized scanner for pattern and character rec. Onishan Studies /WH Hylaman and LA Ka. Mensky, Bell Telephone Lab. File searching using variable length keys /RDLA. Brian Deas, U.S. Naval Ordnance Lab. 1959 Electronic Components Conference. Benjamin Franklin Hotel, Philadelphia, PA. May 6, 7, 8, 1959. Session on High-Speed Data Processing. May 6, morning. Functional Components /RJ Sipser, IBM Corporation. Electronic Components for Future Computers /NM. Above Taleb, IBM Corporation. Magnetic Domain Switching in Evaporated Magnetic Film /David W. Moore, Servo Mechanisms, Inc. The Fabrication and Properties of Memory Elements. Using electrodeposited thin magnetic films of 82 to 18. Nickel Iron /IW Wolf, H.W. Katz, General Elec. Trick Electronics Laboratory, and A.E. Brain, Stanford. Research Institute. Correction. In the January, 1959, issue of Computers and Auto Machine, in the article Symbolic Logic and Automatic Computers, Part 3, on page 19, on the last line, a tilde, dash dash, should be inserted before the expression XM. On page 20, left column, line 6, the same insert should be made before the same expression, and again on line 12. Our thanks to William F. Culleton of Niagara Falls, NY, for catching these 3 errors. 15. Make your tabulating. Department a Service Department. Edmund W. McNamara. Ed McNamara Associates. Bridgeport, Con. Students analyze the evolution of electronic data processing into certain stages of development. One of the early stages pictures the giants of industry, the large institutions and utility companies, and the government pioneering in the use of electronics against a backdrop studded with many pronounced question marks. While off to the side, the smaller, more conservative, more timid managements wait for the first full audit of results BEF9 they take any active step to become involved with the spectacular and expensive new tools of data processing. Some of these managers await the returns with eager anticipation. They seek justification for going out on thin ice in hopes of finding solutions to their clerical problems. Others are far less eager. In fact, some of them hope that the new equipment and methods will prove to be failures so that they can justify a continuation of their old ways and not muddy the water of their existing systems, at least not until their own personal retirement from work has excused them from the responsibility for action. Reports on computer applications. Meanwhile, the reports roll in. In some ways they are encouraging. Yet in many respects there is an emphasis on the negative, and an air of caution. For example, there is the recently published Computer Use Report by the Systems and Procedures Association's Empire State Chapters Research Committee. This was Pub. Listed by the Systems and Procedures Association, LN. Of Scott Building, Detroit, Michigan, in 1958, 12 pages long. It's a statistical information release, covering 281 replies to a questionnaire. 82 organizations reported. Applications in service. The total number of computers involved in the study is 203, about 15% of the total. Medium and large-scale computers in use as determined by a recent census. Table 1 analyzes about 270 applications accepted for electronic computer operation, 82 companies reporting. Table 2 covers about 160 applications rejected, 63 companies reporting, 23 of which have applications in service. 5 more tables analyze occurrence of applications by size of firm, industry, etc. 16. This report, however, has the following introduction. Information on the success or lack of success of the use of electronic data processing equipment has, up to this point, been somewhat vague. To the best of our knowledge, no specific figures have been released from any source that can be used to determine with any accuracy the acceptance or rejection of such equipment. We believe that this report contributes to help fill this void in the field of electronic data processing. In the section devoted to applications rejected, the rejections are analyzed as to when they were rejected, such as during the study, after study, in the programming stage, and so on. And then the reasons for rejection are listed as follows. Too costly. Volume of data too large. Volume of data too small. Routine has too many exceptions. Programming too difficult. Lack of reference to account history. Inadequate input-output equipment. Inadequate input data sources. Fear of equipment obsolescence. Lack of continued top management, support. Lack of employee cooperation. Memory capacity too small. Access time too high. Excessive downtime. Underlying reasons for rejection or failure. Psychologists tell us that there are 2 reasons for everything, the obvious and the underlying. Perhaps this explains why 2 of the major reasons for rejection and ultimate failure are not even mentioned. Nor is their omission a reflection on those who compiled the report. The 2 major reasons I refer to are 1. Failure to do sound systems analysis before forging ahead into electronic mechanization. 2. Failure to establish proper operating policy as to organizational location and role of the data processing function. On this point, we might consider a few significant excerpts from another recent publication, the RAM Myth, April 1958 issue of EDP Analyzer, by Canning, Sisson, and Associates. With all the excitement about large volume random access memories for EDP systems, we think the time has come to add a few words of caution about them. To state it bluntly, we think that RAM memories are heavily booby-trapped for the unwary. We feel that only a few of the many orders on the books for RAM systems are really valid applications. The answer to the proper use of RAMs is, of course, HIG quality systems plans. Equipment always is a poor substitute for thinking. Computers and Automation for March, 1959. POGO is a new programming system that combines the use of simple, easy-to-learn commands with all of the G1S's machine language power and speed. A fixed-point compiler, POGO recodes a simple state meant of a problem in machine language with all commands stored in optimum memory positions. Thus, a programmer with very little training can write high-speed production programs. For the first time in a low-price computer, a set of fully self-contained automatic programming systems is available. Pogo, with its ability to convert simple commands into fast and powerful machine language programs, and the already famous Intercom 1000 interpretive system, with its extreme programming simplicity and speed of preparation. Asterisk program optimizer for 6 to 15 operations. Automatic programming 0-5. Digital computer. Pogo commands are very similar to those used for Intercom 1000. The principal difference between the two systems is that Pogo, unlike Intercom 1000, compiles an optimum machine language program and reproduces it for repeated use. Computing speed is also increased, since no interpretation is required during computation. While floating point Intercom 1000 is ideal for open shop problems, Pogo may be preferred for production problems that must be solved repeatedly at high speed. In Pogo, data is handled in decimal form. 17. Accumulator registers are available, as well as 12 index registers, which can be used to modify the effective address of any command. Additional data on the G15, Pogo, and Intercom 1000 will be sent on request. New program stored on punched paper or magnetic tape for repeated use. Division of Bendix Aviation Corporation, Department DI Los Angeles 45, California. Computers and Automation for March, 1959 feet 17 inches. Getting back to the two major reasons cited above for rejection and failure, my experience tells me that these are perhaps the two most serious reasons. Yet they are the ones least discussed or admitted by official spokesmen of companies engaged in electronic data processing programs. You get much of your information off the record. Much of it must be deduced. Here is a case in point. Inadequate systems work. A large, national organization solicited help in June of 1958. They wanted to hire a systems man. The sense of my questions and their answers follows. Q. What is this man to do? What will be the scope of his job? A. He will have to hire and train assistants in programming and be ready for the installation of a medium-scale computer. Q. To whom will this man report? A. We're not sure yet. Q. When is the computer scheduled for delivery? A. Next December. Q. 1959? A. No, no. This year, 58. Q. Is this a basic computer, or? A. It is the basic unit first and tape units will be delivered in 1959. Q. Do you have anybody working on systems now? A. No. Q. Who has done the systems analysis? A. Nobody, that is why we want to hire a systems man. Q. Who chose the computer? A. An executive whose knowledge and background in the field was slightly above zero. Q. Who advised this executive? A. The equipment salesman. Q. Who determined the feasibility? A. The equipment salesman. What would you consider are the chances of success in this installation? If it fails, what do you think will be recited as the reason for failure? Lack of employee cooperation? Memory capacity too small? 6 months later I revisited the company whose computer was due in December 1958. I found the computer installed in a room far removed from the tabulating department. The floor there wouldn't hold the weight of the computer. The computer had been in for 2 weeks. It had actually been running, but not very much. 3 young service engineers, with a full library of charts and diagrams, were still tinkering and experimenting. The harried systems man told me he had been working all hours trying to get the thing running, and was busy explaining to a member of management that there are mechanical bugs, etc., etc. Operating policy on role of data processing function. Perhaps some organizations can get by without classy. So let us consider the second of the 2 major reasons mentioned: failure to establish adequate operating policy as to the place and role of the data processing function. Since a great number of computer applications are an outgrowth of punch card tabulating functions, let us concentrate our attention back in the tabulating department and inquire immediately: is your tabulating department a service department? 18. There are many illogical situations in business offices. Think of the systems function, fettered under the jurisdiction of an old-school accounting officer. Or think of the tabulating department used as a tool at the whim of the controller, keeping only the records he wants kept, making only the reports and analyses that serve his purposes, actually providing an imbalance of information which distracts management attention from important matters and gives birth to a cardinal sin of data processing: duplicate records. These duplicate records are maintained by each division as a defense against the highly mechanized record keeping in the controller area. Let us not carry this illogical philosophy and thinking into computer installations, if we want success. One of the best insurances against this carryover of illogical thinking is to make your tabulating department a service department now. Overloaded tabulating department. Writing in Systems Magazine, Vincent P. Connolly observed a sudden demand for a tab report by the executive committee of a large steel mill confronted its comptroller. The chore, accepted as routine, revealed that the tab department on 3 shifts was working just about to capacity. Investigation showed that any employee in the organization on the level of supervisor could requisition a machine tabulation job, while the tab accountant had no discretion, only a squawk about taking it on. This far from healthy situation is not uncommon. Underloaded tabulating department. In other companies we find a deplorable situation, which is the opposite of the above. The tabulating department is on a 1-shift basis and overtime is frowned upon. In this situation the machine accountant, through his superior, exercises what may be too much discretion, to the extent that the services of the electric accounting machines are denied to legitimate users. In some situations desirable reports either are done by longhand methods or on some cumbersome office machine, or not done at all. Such operating conditions emphasize T4E need for an Intelligent perspective in relation to the use of tabulating equipment, a perspective and an approach which help to furnish maximum service in the issuance of essential reports and analyses, on time and at minimum cost. In one medium-sized company whose tab department was on a one-shift basis on the controller's department, it was found that their loaded to the hilt situation not only denied the company the clerical savings of mechanical preparation of reports, but it presented a serious roadblock to any unemotional, open-minded approach to the possibilities of integrated or electronic data processing applications. It was recommended that if they were ever to get into a position to benefit from integrated application of machines to paperwork, they must first of all break the roadblock. Basic principles. To begin with, management had to agree that in the area of control reports for management there are three: computers and automation for March, 1959. Main considerations: 1. The objective of the report. 2. The content or requirements of the report, and 3. The cost of preparation, issuance, and use of the report. Next, a review of policies showed that it was explicitly not their accounting policy to charge individual departments for the reports that were prepared specifically for them in the tabulating section. The rental cost of equipment, supplies, and salaries of operating personnel were being charged, against a budgeted allowance, to the factory accounting department. It was pointed out to management that this lack of specific accounting charges for reports defeats the establishment of sound requirements, specifications, and economic justification for reports. We were able to illustrate how some reports were being run simply because the right guy had asked for them, or someone had happened to ask for them at the right time, or because they always ran that report in tabulating accounting charges for services performed. We stressed that tabulating work is of a service nature, and that the concept of service cannot be properly developed if accounting charges are not made for services performed. Furthermore, we pointed out that even an approved report on the approved list suffers if specific accounting for services rendered is lacking. The following two paragraphs from our report to management cover this point. To get a concrete picture of the type of problem created by your present policy, let us consider the area of statistical sales reporting and analysis. From a sales administration standpoint, sales management rightfully has the authority to realign geographic territories, to reassign salesmen, or to reassign accounts. The manner and degree to which these steps are taken has direct bearing on the cost of administering your machine accounting section without a charge. For service concept, your machine accounting section is subject to conditions which encourage improvisation and shortcuts, and which require costly manual operations and extra difficult schedules, all of which reflect unfavorably upon the machine accounting section and on the equipment used. Because all work performed in the machine accounting section is charged to the factory accounting department, it puts them under the pressure of their departmental budget. This produces a tendency to do the minimum, and often results in unsatisfactory sales reports coming off the machines, of which there is ample evidence. We suggested that as a matter of philosophy and policy, any department of the company should have equal right to request a report or an analysis that would help them in their departmental operations. Based on this request, a cost of performing the service would be Computed by the machine accounting section. If the using department agreed to pay the cost and manage, meant gave the report the blessing, then the report would be produced on a service basis by the machine accounting section and charged, accounting-wise, to the benefiting department or departments. Price tags on reports. Based on this thesis, management agreed to change policy to conform to a service concept. To implement this, we worked out a set of rates per hour to be used as standard service charges for tabulating reports. See Appendix A. We also established a budgeted allowance for each division against which reports would be charged, with the division head's approval. Now each report has a price tag. The using department pays the price. A re-evaluation of existing reports in terms of what it costs versus how useful it may be, is serving as a real control over the number and kinds of reports being turned out by the tabulating department. More important, having removed the roadblock, the company is now in a position to go ahead with plans for future use of their equipment, interim and long range. To this end, they have established an Office Automation Committee. The work of this committee is to review present procedures and methods and examine the possibilities of instituting integrated data, or electronic data processing methods into their reporting processes. If they do develop a feasible plan, they know that they will have a greener light based on the merits and economic justification of the proposed application. They will not have to worry about being stifled by an unscientific situation such as observed by Mr. Connolly. Appendix A. Schedule of service charges for IBM tab reports. Key punch alpha. Key punch numerical. Key punch numerical. Key verifier. Collator. Sourcer. TAB 402. Reproducer 514. Calculator 602A. Rental cost excise. Monthly yearly tax total 4,480. 48,528. 35,420. 42,462. 35,420. 42,462. 5,600. 6,660. 101,200. 121,220. 55,660. 66,726. 445,280. 528 5,808. 110 1,320. 132 1,452. 245 2,940. 294 3,234. 13,320 1,332. 14,652. Labor at 1.80/HR plus 160% overhead equals 4.68. Labor at 2.10/HR plus 160% overhead equals 5.46. Hourly star cost 0.44. 0.39. 0.39. 0.55. 1.10. 0.61. 4.84. 1.21. 2.70. Based on 60% efficiency normal operation, 1,200 hours per year. Asterisk monthly rental figures subject to change. Computers and automation for March, 1959. Labor total 4.685.12. 4.685.07 4.685.07 4.685.23 5.466.56 5.466.07 5.4610.30 5.466.67 5.468.16 19. Survey of recent articles. Beginning in this issue, we plan to publish frequently a survey of articles related to computers and data processors, and their applications and implications, occurring in certain magazines. We hope to cover at least the following magazines, beginning with issues dated January 1st, 1959, or later. Automatic Control, Automation, Automation and Automatic, Equipment News, British Business Week, Control Engineering, Datamation, Electronic Design, Electronics, Harvard Business Review, Industrial Research, Instruments and Automation, ISA Journal, Proceedings of the IR, Management Science, The Office, Scientific American. It is not easy to look into more than 15 magazines each month, and make a search. The purpose of this type of reference information is to help anybody interested in computers find articles of particular relation to this field in these magazines. For each article, we shall publish the title of the article / the name of the author, / the magazine and issue where it appears / the publisher's name and address / 2 or 3 sentences telling what the article is about. Wad brains ponder mechanization of thought processes / G mobile / auto machine and automatic equipment. News, Yale. 4, number 5, January, 59, p. 929 / ANAE News, 9, Gough Square. Fleet St, London, EC4, Eng. A report of the Teddington, Middlesex Symposium on Advanced Electronic Machines which perform logical operations and certain other intelligence operations. The findings and opinions of certain international scientists are cited. How electronics controls depth of ains. Thea / J. Weldon Belleville, MD. Sloan Kettering Institute, New York. And G. Emichira, Chief Engineer, in Industrial Control Co., Lindenhurst, NY. / Electronics, Volume 32, Number 5, January 30, 1959, p. 43 / McGraw-Hill, 330 West. 42 St, New York. Automatic controls may be used to check continuously the border of wakefulness of a patient undergoing a surgical operation. A servo-driven automatic system replaces the human anesthesiologist in the administration of anesthetic agents. It regulates the amount of anesthetic being administered. Mechanization in a British publicly Brary / John Grindrod / The Office. Volume 49, Number 2, February, 59, p. 16 / The Office, Office Publications Incorporated, 232. Madison Ave, New York 16, NY. The use of both marginal punched cards and machine tabulating cards in London's libraries, how the systems are effectively used, and how much they cost. Digital system positions shafts over phone line / RB Palmiter, Chief Electronics in Group, Amer. Mock End. Foundry Co. /Electronics, Volume 32, No. 7, February 13, 1959, p62/McGraw-Hill. 330 West 42 St., New York. A modulator superimposes positions of master shaft expressed in digital codes on a carrier wave, mixes the modulated signal with control information, transmits the composite signal at the rate of 750 bits per second. An amplifier and demodulator reproduces the original signals, which are then compared with positions of slave shafts expressed in digital codes. Differences are then converted into analog signals correcting the slave shafts. Magnetic drum provides analog time delay. H.L. Daniels and D.K. Samp. Son, Remington Rand Univac, Division of Sperry Rand Corp., St. Paul, Min. Electronics, Yale. 32, Number 6, February 6, 1959. p44/McGraw-Hill, 330 West 42 St. New York. A relatively uncomplicated drum recording system has been developed to make analog simulations in designing continuous processing systems, which provide a time delay in a highly stable SYS-TEM, applicable also to tape. Precision of 0.1% is exceeded between record and played back low frequency analog voltages. Tape recording system speeds data processing. Wei Dongwu, Data Matic Div, Minneapolis, Honeywell. Regulator Co., Newton Highlands, Mass. /Electronics, Volume 32, Number 6, February 6, 1959, p56/McGraw-Hill, 330 West 42 St., New York. The use of a technique for recording pulse duration and a 31-channel block format give large information content, while minimizing dead space and effect from tape skew, plus the ability to record on individual blocks. These unique uses of magnetic tape enable a data processing system to handle information at a rate of 40,000 alphanumeric characters per second. Automatic failure recovery in a digital computer. R.H. Doyle, R.A. Meyer, and R.P. Perdowit / IBM Journal of Research and Development, Volume 3, No. 1, January, 59, p2 / IBM Corp., 590. Madison Ave, New York 22, NY. A program which enables a complex digital data processing system to discover and correct its own errors. The fix program compensates for its errors, achieving recovery with a negligible loss of time. Some methods of the program are discussed, as well as reliability techniques, program design, and recovery procedures. On the mathematical theory of error correcting code. H.S. Shapiro, and D.L. Slotnick / IBM Journal of Research and Development, Yale. 3, Number 1. January, 59, p25 / IBM Corp., 590 Mad. Eisen I, New York 22, NY. A discussion of the use of Hamming codes for efficient transmission of binary data over a noisy channel. Hamming reconstruction considered error free signaling over a channel which corrupts no more than one binary digit in each sequence of length n. The authors Consider the problem for channels which can corrupt a greater number of digits. An experimental modulation demodulation scheme for high-speed data. Transmission/eHonors/IBM. Journal of Research and Development. YIL. 3, No. 1, January, 59, P74/IBM. Corp. 590, Madison Avenue, New York. 22, NY. The theoretical and practical problems involved in a system designed to deter mine speed and reliability limitations on transmitting binary data over telephones. Designed for speech transmission. Probe. Please turn to page 25. Computers AMI Automation for March, 1959. All new, all transistorized. The only all-purpose medium-scale data processing system that starts economically, expands with your needs, and cannot be outgrown. H. Plus. Computers and Automation for March, 1959, 2.t. The all-transistorized Honeywell 800 is the only computer that gives you the ability to process up to 8 programs simultaneously, each independently written and automatically controlled. No complex and costly programming is necessary to utilize the full efficiency of the Honeywell 800. A single powerful control unit supervises each and every independent operation speeding in parallel. This achievement we call automatically controlled parallel processing. Its practical economic advantages are sizable for workloads large and small, business or scientific. For example, you could run off a payroll, update your inventory and schedule production all at the same time. And all as independent jobs. And if your engineering staff needed to solve a complex scientific problem in a hurry, you could put that on Honeywell 800 too, while your data processing is going on. All these operations are meshed into a machine determined schedule, always geared to utilize Honeywell 800 to its maximum efficiency. The central processor does not wait for relatively slow mechanical operations such as card reading or printing. All programs are automatically dovetailed to fill in dead time when the computer would otherwise lie idle. Honeywell 800 thus introduces heretofore unimagined simplicity, efficiency, and economy in this vital area of programming and scheduling. Your entire day's work can now be accomplished smoothly and on schedule with several of your key programs operating in parallel and automatically controlled. The profitable use of the basic Honeywell 800 system begins far down the ladder to include relatively small volumes of work, and it can be utilized to accommodate your company's growth for years to come. This extraordinary capacity can be expanded at any time in small steps and at small cost. No management need make such additions until they can efficiently and profitably use them. And you can't outgrow Honeywell 800. Its tremendous potential capacity plus its ability to operate more than a dozen data processing devices simultaneously make it your profitable partner indefinitely. And with Honeywell 800 you will never again have to face the cost of reprogramming. Does all this sound costly? Honeywell 800 is competitively priced with other systems. In a working day it can process more data per dollar than any other computer. Both the equipment and the programs of Honeywell 800 are backed by years of experience, and the caliber of service which users of Honeywell's DAT-matic 1000 have come to expect. 22. Vital statistics of the Honeywell 800. Word definition: 12 decimal digits, 8 alphanumeric characters or 48 binary digits. Memory size: 4096 to 16384 words. Order structure: 3 address. Internal operating speeds: single active address operation 60,006 per second. 3 address operations 30,000 per second. Information transfer rate 140,000 words per second. Accumulations 125,000 per second. Input-output: magnetic tape, %wide. Speed 96,000 decimal digits per second per unit. Tape capacity up to 20 million decimal digits. Maximum of 8 units reading and 8 units writing in simultaneous operation. Standard card reader 240 cards per minute. Maximum of 8 units in simultaneous operation. High-speed card reader 750 cards per min. UT, maximum of 8 units in simultaneous operation. Standard printer L50 lines per minute, max. Minimum of 8 units in simultaneous operation. High-speed printer 600/900 lines per minute. Maximum of 8 units in simultaneous operation. Standard card punch LU cards per minute. Maximum of 8 units in simultaneous operation. High-speed card punch 200 cards per min. UT, maximum of 8 units in simultaneous operation. Standard features: 1 parallel processing of up to 8 independent AND programs. 2 parallel operation of input-output devices. 3 binary and decimal arithmetic. 4 indexing. 5 word masking. 6 tape reading in either direction. 7 fast tape rewind. 8 online inquiry processing. 9 multifunction instructions. 10 orthotronic control. 11 automatic programming routines. 12 library routines. 13 by sequence operation mode. Optional features: floating point arithmetic, random access storage, paper tape input-output equipment. How to get more facts. If you would like more information about Honeywell Boo, please let us know. We will send you complete details by return mail. Right. Minneapolis Honeywell, DAT Division. Department A, Newton Highlands 61, Massachusetts. Honeywell JJDAT Natick. Electronic Data Processing, Computers and Automation for March, 1959. HONEVLNELL Boo. Asterisk. Do up to a different independently programmed jobs. Simultaneously, business, scientific, or both. Asterisk. Process many business jobs independently in no more time than it takes to do the longest job alone. Asterisk. Solve complex scientific problems more efficiently than computers marketed for this purpose. Asterisk. Process small volume applications economically. Asterisk. Expand capacity in small, economical stages. Asterisk. Grow without limit to meet your future needs. Asterisk. Grow without reprogramming, with its heavy costs. Asterisk. Process more data per dollar in a working day than any OT/her system. Honeywell 800 is priced competitively with other systems. It cuts costs for floor space, air conditioning, and power, and is backed by Honeywell's electronic experience and the type of service you have come to expect from Honeywell. Computers and Automation for March, 1959. Honey VWELL 800, continued. Opportunities at Honeywell. For experienced methods analysts and engineers. The overwhelming acceptance of Honeywell 800 has created immediate openings for ambitious and imaginative people with experience in the field of electronic data processing. If you are looking for the opportunity to make substantial contributions to advances in this field, if you seek the recognition that comes through performing difficult assignments well, if you enjoy working with competent, stimulating associates on projects that have solid management support, consider the following. Systems and methods. Analysts. Systems and methods analysts assist sales engineers in analyzing and developing potential customer applications. They provide the necessary training and guidance to assure optimum utilization of the system, combining a knowledge of the customer's office systems and procedures with their command of the Honeywell 800 system. Formal background desired. High academic standing in business administration or a field of science. Data processing or computer programming experience desirable. Send resume to systems analysis engineers. Systems analysis engineers are responsible for advanced logical and systems design and evaluation, the design and implementation of compilers, utility routines, operating procedures for automatic routines, library subroutines, test routines, and new automatic programming techniques. Formal background desired. High academic standing in a field of science. Data processing experience and advanced degrees desirable. Design and development engineering. Depending on training, experience, and qualifications, systems, circuit, and logical design projects are available involving the advanced application of transistors, cores, tubes, diodes, and a variety of magnetic devices, electronic and mechanical design of manipulative memory and peripheral conversion equipment, component evaluation and design, or the design of complex digital systems test equipment. Formal background desired. Electronic engineering, physics, mechanical engineering. Personnel Director, Department 10. Minneapolis Honeywell Regulator Company. DATmatic Division. Honeywell. DATmatic. Electronic Data Processing Newton Highlands 61, Massachusetts. 24 CompUGERS and Automation for March, 1959. Survey of recent articles. Continued from page 20. Lems such as impulse noise, phase distortion and choice of modulation scheme are covered, while performance of the equipment is reported with the reliability ties experienced at 600, 1000, 1600, and 2400 bits per second. Fast Automation, Britain Salvation / J.W. Murray / Automation and Automatic Equipment News, Volume 4, Number 5. January, 59, p. 904 / Automation and Automatic Equipment News, 9 Goff. Square, Fleet St, London, EC4, Eng. The seventh and concluding article in a series by the author on the problems of automation. The series dealt with comparative economic and political problems in the United States, Great Britain, and The Soviet Union. This article discusses future prosperity based upon automation. Diffusion attenuation, Part I/JA. Swanson/IBM Journal of Research and Development, Volume 3, Number 1, January 59, P13/IBM Corp., 590 Madison Ave, New York 22, NY. The problem of calculating the attenuation of signals consisting of compensated space charges moving in an electric field of general, but prescribed, form is solved by perturbation methods. An iteration process is developed for obtaining the general solution in the one-dimensional case. Asymptotic formulas for attenuation and phase shift are derived. A survey of British digital computers. Introduction. In the United Kingdom, as, in the United States, most of the innovations in design, development, and use of computers, have come from university and other scientific research laboratories. Sometimes, these studies were supported by government or interested manufacturers. As most of us know, the first automatic digital calculator was designed by a British subject, Charles Babbage. Though constructed in parts, his engines were never completed. It was only about 1944 that, in the US, H.H. Aiken set the first digital computer into operation, the IBM ASCC or Mark I, Harvard University. Since that time a lot of pioneer work has been done in the United Kingdom. The first computer using a magnetic drum storage, the ARC, was constructed by A.D. and K.V. H. Booth, both of Birkbeck College. A prototype SEC and the APE X.C. series followed later. The first British computer with delay line storage, EDSAC I, was constructed by M.V. Wilkes of Cambridge University. Recently an expanded type, EDSAC II, with magnetic core storage has been completed. Another computer with delay lines, the well-known Pilot ACE, was completed at the National Physical Laboratories, the counterpart of the U.S. National Bureau of Standards. Later on this Part I. Joseph L. F. de Curve Research Laboratories. Gevaert Fotoproducten N.V. Mortsel, Belgium. Computer WS replaced by an engineered version, while Pilot ACE was bequeathed to the British Science Museum for exhibition. An expanded Type ACE has been completed recently. The use of cathode ray tubes as store element was pioneered by F.C. Williams of the Manchester University in his Mark I, an X. Pondade type, Mark II, and an X. Perimental transistor machine followed soon. Like EDSAC II, Mark II has a magnetic core storage. From all these experimental Mach-E several commercial versions were derived. It must be noticed, however, that in Great Britain the total number of computers installed or on order is only about 300. 1958. This number is small, compared with that in the US, but on the European computer market, Great Britain is undoubtedly leading. Readers of this journal receive yearly a list of information about what is available in the computer field. The computer directory and buyer's guide embraces only the US products, and those overseas. Products, represented in the US. Details about British commercial computers are given in some journals and other publications related to the field, but so far as we know, a complete description has never been published in the US. It is the purpose of this repon to do so. Most of the information was Computers and Automation for March, 1959. Assembled by the author as a member of a course on digital computers, or organized at the end of 1957 by the British Council, and as a visitor to the Electronic Computer Exhibition, held at London, Olympia, in November-December 1958. The author is indebted to the direction of the Gevaert Fotoproduct 10 NV, Moncel, Belgium, who made this study possible. He wishes also to thank the manufacturers who checked the information given. British C. Computers and Manufacturers. The British Tabulating Machine Co., Ltd. Hyde Park, London. The company has been marketing Hal Aerith punched card equipment, 80-column cards, for nearly 50 years. Allied with International Bus Innes Machines Corporation, the company became independent about 10 years ago. Recently BTM has entered into association with the Laboratory for Electronics, Boston, Massachusetts, and with the General Electric Company, Kingsway, London. A proposed merger between BTM and PowerShell should be finalized in 1959. Since 1951 a series of electronic calculating punches, the most recent being the Hal Aerith Type 555 electronic calculator, has been developed. About 15 555s have been delivered so far. In 1953 an electronic 25 computer for scientific calculations, HEC2, was introduced to satisfy the needs of business and industry. HEC4, now called HEC Type 1201, has been constructed. A similar computer, but with expanded storage capacity, is the HEC Type 1202. About 50 HECs have been installed or are on order. Data processing systems also have been designed. The first, Type 1400, will be completed in the near future. Hal Aerith 555. Controlled by panels. Operation mode. Serial parallel. Number base, binary. Word length, 10 decimals plus. Sign. Program, 150 steps, 3 address in. Struct ions. Extraction of square roots. Automatic. Store, magnetic drum. Capacity, 105. Words, 5 tracks of 21 words and 1 additional track as input, output buffer store. Speed, 3000 RPM. Average access time, 10 milliseconds. Input/output, 80 column cards, 100. Cards per min. Operation speeds, average 1 millisecond for addition and subtraction, 18 milliseconds for multiplication and 55 ms for division. Power consumption, about 8 kVA floor. Area occupied, 40 square foot. Price, approximately £25,000. HEC 1201 and 1202. Operation mode, serial. Number base. Binary. Word length, 40 bits, including UD. ing sign. Order code, 1+1 address type. 1 word. Store, magnetic drum. Capacity, 1024. Words, HEC 1201, or 4096 words, HEC 1202. Speed, 3000 RPM. Average AC. Ses time, 10 milliseconds. Input, card reading unit of a tabulator. 100 cards per min, alphanumeric. Output, printing unit of the tabulator, 100. Alphanumeric lines of 100 character per min. Or gang punch, 100 cards per min. 80. Column cards are used. Sterling conver. Xeon is automatic. Operation speeds, 2.5 milliseconds for addition and subtraction, including instruction. 20 milliseconds for multiplication, average, and 50 ms for division, maximum. Power consumption, 11 kVA floor. Area occupied, 57 square foot. Price, HEC 1,200 and 133,000 pounds. Type 1400. Operation mode, serial parallel. Number. Base, binary decimal. Wand length, 11. Digits plus parity digit. Word transfer. Time, 16 microsec. Order code, 3 add. Dress type, 1 word. Immediate access store, magnetic cores. Capacity, 100 words. Backing store, mag. Netic drum. Capacity, 11,250 words. Speed, 6,000 RPM. Average access time, -5 ms. A Decca twin magnetic tape unit. May be added. Input, 0.80 column punched cards, 600. Cards per min. Output, high speed. Printer, 400 lines per min. Basic order time of the arithmetic unit is 0.016 milliseconds. Multiplication speed is up to 0.850 milliseconds. A multiply divide order RIO requires up to 1.65 milliseconds. 26. Price, expected to be from £100,000 to £150,000. Later machines will include an IM.DIT access store of up to 1000 words. Up to 5 additional drums, additional magnetic tape units, additional card readers. And online printers, punched card output. Paper ape readers and punches. AutoIt Brothers Ltd. Compo Mock. DIV. Boehmwood, Hertfordshire. A part of manufacturing analog computers, like GPAC, the company has developed a series of digital computers. A nickel delay line. Store machine, Nicholas, was completed in 1950 and is still in operation for internal work. The commercially available computers were developed from the Elliott 401, which was completed in 1954 and is now operating at the Rothamsted Agri-Cultural Research Station. The production version, Elliott 402, was one of the first British machines in which an extensive use was made of plug-in units, about 95% of the electronic equipment. 2 other scientific computers, Elliott 403 and 404, followed soon, and a data Sessing machine, Elliott 405, was designed. The object of the 405 is to be a flexible system whose differ and possible arrangements can evolve as requirements dictate and as technical advances allow. Several have been completed and a sales agreement was concluded with the National Cash Register Co. A transistorized small-scale magnetic core store computer, National Elliott 802, has been completed recently. It was designed for business, scientific, process control and data logging applications. About 45 Elliott computers have been delivered or are on order. Elliott 402. Operation mode, serial. Number base. Binary. Word length, 32 bits, including sign digit. Point working, fixed, 402E. Or fixed and floating, 402F. Instructions, 1+1 address code, 1 word. Addresses can be modified by use of 7 B-lines. Order code and operating speeds are the same for both NXED and floating point calculation. Immediate access store. 17 single-word nickel delay lines, including accumulator. Main store, magnetic drum. Capacity, 4,976 words. Speed, 4,600 RPM. Mean access time, about 6.6 ms. 2 magnetic film units can be connected. Each rifle holds 281,600 words. Input, 80 column PNCHED cards with photoelectric reader, 400 cards per min. Or 5-hole paper tape, Ferranti, 180 char per SEC. Output, 5-hole paper tape, 2 character per SEC. Standard Hall Aerith or IBM card readers may be connected. Operation speeds, including time taken for decoding of order 0.204 milliseconds for addition and subtraction, 3.376 milliseconds for multiplication and division. Power consumption, 7 kVA, 402E, and 11 kVA, 402F. Floor area occupied, about 44 square foot. Minimum price, £25,000. 402E, and £35,000, 402F, magnetic film units not included. National Elliott 405. Operation mode, serial. Number base. Binary. Word length, 32 bits, including sign digit. Instructions, 1 address type. 1 half word. Quick access store, nickel delay lines. Standard capacity, 512 words. Average access time, 0.8 milliseconds, 3 words are in. Diet access. Main storage, magnetic drum or magnetic disk. Capacity, RIO. Respectively 4,096 and 16,384 words. Transfer, in blocks of 64 words. Average access time for a block, 19.5 milliseconds, drum, and 26 milliseconds, disk. During transfer the machine is capable of carrying out other work. Magnetic film units are optional. The films are 35 mm wide and 1,000 feet long. Their capacity is 281,600 words. The film units are connected with the computer over control units with a quick access buffer of 64 words. Transfer is done in blocks of 64 words. 1 to 4 con. Trol units can be connected and each unit can control 1 to 4 magnetic film units. Input, 80 column punched cards, 400 cards per min, or 5-hole paper tape, fur. Ranty, 180 character per SEC. Up to 3 chan. Nels may be used. Output, 5-hole paper tape, 25 or 60 character per SEC, magnetic. Film, 300 character per SEC, or electric type. Writer, IO character per SEC. Output by punched cards is available. Up to 4 output channels may be used. Addition of high-speed paper tape reader, 500 or 1000 character per SEC, and punch, creed. 300 character per SEC, has been developed. Offline output from the magnetic films is on paper tape or high-speed printers. Operation speeds, including instruction. 0.153 milliseconds for addition and subtraction, 3.3 ms for multiplication and division. Power consumption, 15 to 35 kVA. The floor room required for a typical install Lashin is about 1,200 square foot, price £30,000 and up. National Elliott 802. Operation mode, serial. Number base. Binary. Word length, 33 bits, including sign digit. Instructions, 1 address type. 1 half word. Store, magnetic cores. Capacity, 1024. Words, 4 words of fixed orders. Any location may be used as B modifier. Input, 5-hole punched tape, Ferranti. Up to 170 character per SEC. Output, 5-hole punched tape, 25 character per SEC, subs. Quently interpreted by typewriter, 10 character per SEC. A punched card reader. Additional tape readers and punch, man. UAL keyboard input, analog and digital. Recording mechanisms are optional. Operation speeds, including instruction. 0.612 milliseconds for addition and subtraction. 21.4 milliseconds for multiplication and division. Power consumption, 2 kVA floor area. Occupied, 40 square foot, price, basic RNA. Chine £20,000. Computers and Automation for March, 1959. Save design time, avoid assembly headaches with General Electric custom designed DC power supplies. General Electric can meet your power supply requirements. Your requirements from individual packages to complete systems. These can be supplied from 1. Completely engineered equipment in stock, 2. By custom packaging of components, or 3. With completely new designs. Whatever your problems, General Electric can handle your power supply system responsibility and save you design time and assembly problems. For more information, contact your nearest General Electric apparatus sales of FICE or write to General Electric Company. Section B535-1, Schenectady, New York. Progress is our most important one. NF.LV, F. General Electric. Computers and Automation for March, 1959. 27. 28. Sewing TOEFL J's problems today Burroughs 220 Computer. In scientific computation and business data processing, the new Burroughs 220 is delivering tangible results today. Linking a powerful digital computer to equally powerful input-output subsystems, the 220 offers balanced performance at the lowest application cost. Its expandable core memory, built-in floating decimal arithmetic, vast data file, magnetic tape capacity and the multiple card processing ability of Carditron make this the most powerful system available in the medium price field. The 220 is just one part of a complete line of advanced Burroughs electronic data processing equipment, now in production, now at work in hundreds of installations, supported by an outstanding team of computer specialists. Write today for 220 brochure, Electrodata Division, Pasadena, California. Burroughs Corporation. RNEW Dimension/in Electronics and Data Processing Systems. Computers and Automation for March, 1959. EMI, Electronics L10. Hayes, Middlesex. The EMI. Electronics Ltd, controlled by Electric and Musical Indus. Tries Ltd, manufactures electronic instruments, photomultipliers, nuclear health instruments, electronic enlargers, industrial television equipment, machine tool control systems, computers, etc. Both the analog and the digital computer field are covered. The latest development in the analog computer field is EMIAC, a high-speed digital computer, MIDEC 1100. Employing magnetic cores and transistors, has been developed. With its associated input and output equipment and high-speed magnetic tape units, it provides a fully comprehensive and flexible data processing system. The first of the series has been completed in 1958. A new large high-speed data processing system, EMI, December 2400, is being developed in conjunction with the National Research Development Corporation. MIDEC 1100. Operation mode, parallel. Internal number. Bur system, binary. Word length, 36 bits. Instructions, to address type, 1. Word. Computing store, magnetic cores. CA. Capacity, 1024 words. Main store, magnetic drums. Capacity, 8,192 or 16,384 words each. Access time, 10 milliseconds, any reasonable number of drums may be used. Up to 16 ME magnetic tape decks may be added. Read/write speed, 20,000 char per second. Input, 80 column punched cards, AutoIt. 400 cards PCR min, or 5-hole paper tape. Ferranti, 350 character per SEC. Output, 5-hole paper tape, 25 character per SEC. Printer, 100 lines of 100 character per min. High-speed printer, Semastronic, 300 lines of 140 character per min, or teleprinter/ electric typewriter. Output by punched cards can be provided. Each input and output unit has magnetic core buffer. Store. High-speed printers can be supplied to work offline from magnetic tape. Alphanumeric, decimal, and sterling conversion is automatic. Operation speeds, including B-line mode. Specifications and access time to the immediate access store 0.125 milliseconds for addition and subtraction, 1.120 milliseconds for multiplication and division. Power consumption, 5 to 15 kVA. Room accommodation requires 600 to 1200 SQ. Foot price, £100,000 to £200,000 for an average installation. MIDEC 2400. Operation mode, parallel. Both binary and alphanumeric data are processed. All arithmetic operations are performed in binary. Binary word length, 36 bits. Instruction code, to address type, 1 word. Conversion orders to and from binary are provided. Alphanumeric word length. Variable, up to 15 units of 6 characters. 36 bits, per unit. High-speed store, diode capacitors. CA. PACI, 64 words, which can be used as B-lines. Cycle time, 4 microsec. Computing store, magnetic cores. Capacity, 4096 words. Cycle time, 15 microsec. Magnetic core storage is used in offline. Peripheral units and fast start-stop 1-inch magnetic tape, 20 units, to integrate the system. 4-inch wide magnetic tape, 5 units, is used for bulk storage. Both tapes operate at 20,000 character per SEC. Online input, 65 or 80 column punched. Cards, 300 cards per min, 5 or 7 whole. Paper tape, 300 character per SEC, or both. Forms of magnetic tape. Offline input. Keyboards to magnetic tape via input. Units, up to 112 keyboards per unit, and 65 or 80 column punched cards or paper. Tape to magnetic tape converters. Online output, punched cards, 100 cards per min, paper tape, 30 character per SEC. Line printer, 300 lines of 140 character per min, or both forms of magnetic tape. Offline output, punched cards and line printer, eventually a xerographic printer. 3000 lines per min, from magnetic tape. And existing tabulators from punched cards. The central computer operates asynchronously. Most instructions are set up and executed in 25 to 40 microsec. Average consumption, 20 kVA, exclusive of tape unit motors. Floor area, about 200 square feet and up. Price, not yet available. The English Electric Co. Ltd., Kidsgrove, Stoke-on-Trent, staffs. In conjunction with the NPL, National Physical Laboratory, the Nelson Research Laboratories of the English Electric Co. Ltd. designed and developed a commercial computer, universally known as DEUS. Digital Electronic Universal Computing Engine. This machine was based on the original pilot model ACE of the NPL. One DEUS has been installed at the NPL. 3. Are employed by the E.E.C itself for their own research as well as for higher services. About 20 have been constructed for outside establishments. Besides this, the firm has developed a system of logical circuits in the form of standard units which When integrated and fitted with the appropriate control circuits, can be combined to a large range of special purpose computers. DUS. Operation mode, serial. Number base. Binary. Word length, 32 bits, including sign digit. Special facilities incorporated. For double-length arithmetic. Instructions, 2+1 address type, 1 word. Short access time store, Mercury delay. Lines. Capacity, 402 words. Composition, 4 short lines of 1 word, access. Time immediate, 3 short lines of 2 words. 16 microsec average, 2 short lines of. Computers and Automation for March, 1959. 4 words, 48 microsec average, and 12 long lines of 32 words, 496 microsec average. Auxiliary store, magnetic drum. Capacity, 8,192 words, 256 tracks. Of 32 words. Speed, 6,510 RPM. Access to a specified track is given by movable sets of heads. Transfer is done in blocks. Of 32 words, 1 track. Transfer time amounts to 15 milliseconds if the head assembly is not required to move, and to an additional 35 milliseconds if it has first to be moved, but computation may proceed in the meantime. The storage capacity can be extended by connecting up to 4 deca twin magnetic tape units. Input, 80 column punched cards, BTM. Hall Aerith card reader, 200 cards per min. Output, 80 column punched cards. BTM Hall Aerith punch, 100 cards per min. Both can be replaced by IBM equipment. Input and output is operating on 64 columns of the cards. High speed. 5 or 7 hole paper tape input, 850 char per SEC, and 7 hole paper tape output, 30 character per SEC, may be fitted. Operation speeds, including instruction. 0.064 milliseconds for addition and subtraction. 2 milliseconds for multiplication and division. Power consumption, 10 kVAAD up. Floor area, minimum 92 square foot. Price, approximately £56,000, spares included but without magnetic tape units and paper tape equipment. The machine described, DUS MK I, is mainly intended for scientific and technological applications. A later version, DUS MK 2, MKIIA provides 7 extra, long delay lines, is intended to form the sectoral unit of data processing systems. Input and output of this machine is operating on the full capacity of the punched cards. Ferranti Ltd. Hall in Wood, Lancashire. After Professor F.C. Williams and his colleagues at Manchester University had designed and completed 2 experimental computers with cathode ray tube storage, FIR. Wright Ltd. replaced those in 1951 by an engineering version, the FIR. Ranti Mark I computer. A copy of this was installed at Toronto University, Farad, and in 1953 a series of commercial versions was started. The Ferranti Mark I* computers. 7 of this type were made, and in 1956, the construction of a medium Sized machine, the Ferranti Pegasus. Computer, was begun. About 20 of this multi-purpose machine have been installed, and it has been expanded to a data processing system. Furthermore, the first commercial version of a large scientific computer, the experimental Manchester University Mark II, was completed and delivered to this university in 1957. This computer was named Ferranti Mercury, and about 16 have been installed or are on order to be continued. 29. 30. Expanding the frontiers of space technology. Lockheed's Computer Center is one of the largest and most modern in the world. It is concerned with formula and data applications in more than 40 areas of scientific and technical development. The center includes 2 UNIVAC 1103A digital computers with floating point arithmetic, 20 magnetic tape units, card-to-tape converter, tape 40 card converter, 2 high-speed tape printers, Model 1100 Veripjotter, 3100 amplifier, 360 amplifier and 220 amplifier analog computers, 1211 at X17 XY plotters, double ARM 31TX30 XY plotter, and 114 channels of time history recorders. In the solution of complex mathematical problems, the center serves both government and outside commercial organizations. Programs have included strategic and logistic problems, Monte Carlo systems, sales forecasting, personnel assignments, cost accounting, analysis of control systems, stress and flutter, static, wind tunnel and flight test, missile performance, aerodynamics, and trajectories. Digital computers are used in the solution of problems of missile motion, numerical integration of ordinary differential equations, dynamical simulation, wave fitting, and analytical approximation. Analog computers are most useful for the solution of problems concerning flight control, stability, structural analysis, dynamic analysis, and simulation. Scientists and engineers of outstanding talent and inquiring mind are invited to join us in the nation's most interesting and challenging basic research programs. Right. Research and Development Staff, Department C45 962 WEI Camino Real, Sunnyvale, California. The organization that contributed most in the past year to the Advancement Zero/the Art of Missiles and Astronautics National Missile Industry Conference Award /1 at KLJLT Missiles and Space Division, Sunnyvale, Palo Alto, Van Nuys, Santa Cruz, Santa Maria, California. Cape Canavefll, Florida. Alamogordo, New Mexico. Readers, and Editor, S. Forum. Continued from page 6. Necessary philosophy. Here then, we have an example of where the scientist met an impasse, yet took upon himself the responsibility of overcoming it, even though it meant invading another field of knowledge. The same type of thing, I believe, will be repeated at the present time in regard to the destructive power of the atom, if men in other fields do not provide the necessary safeguards, for instance, international governmental affairs, then scientists will again leave their own fields and seek to provide whatever influence is necessary to see that the atom be used for peaceful purposes only. Russian and American scientists seem to work to together with some degree of harmony within the field of science. If together they would flatly refuse to cooperate with their governments in case of war, then the governments might be helpless to undertake a war. In this case the scientist would have the final say. It seems to me that it is the broad scientific views of many Russian scientists that are beginning to soften the governmental agencies in Russia. The same should be true of American scientists. Their influence upon our government is likely to be felt more in the future than it has in the past. The entrance of scientists into governmental affairs is a natural consequence of the great influence science is exerting upon society. The great advantage that America has over Russia is in free interplay and coordination within the different elements of society, while in Russia, such interplay is strictly controlled by a few governmental leaders. Several of the editorial articles printed in your magazine reveal a fresh and broad outlook upon some of the problems connected with science and world affairs. A type of outlook that is seldom found elsewhere. It is for this reason that I am writing. 2. From the editor. Scientists, when they reach out into a new field, bring considerable advantages. 1. A fresh viewpoint. 2. A respect for facts, and a strong desire to find out the true facts. 3. Habits of using logical reasoning and the laws of probability. 4. A capacity to ask penetrating questions. The present importance of operations research and management science, often making use of automatic computers, springs from the entry of trained scientists into new, practical fields in management, business, industry, and war. There is now a big new field for computer scientists to reach out into. This is the field of sensible activities to prevent millions of human deaths from the combination of computing devices, ballistic missiles, and nuclear warheads. The only substantial reason that the United States and the Soviet Union are pouring money into ICBMs and IRBMs is that they can carry nuclear warheads. In fact, the accuracy of an ICBM or an IRBM is not sufficient for a chemical warhead like TNT to make military sense. Computers and Automation for March, 1959. Whether or not a computer scientist reaches out into this new field is mainly a matter of his attitude. This depends on the awakening of thought, reflection, and decision. And let no one believe that millions of Russians will be dead and no Americans, or that millions of Americans will be dead and no Russians. If there is any positive conclusion to be drawn from the mounting supplies of nuclear bombs, ballistic missiles, and guidance systems, if they are ever used, it is this: both millions of Americans dead and millions of Russians dead, including nearly all inhabitants of New York, Chicago, Los Angeles, Washington, Moscow, Leningrad, Kiev, Vladivostok, etc. And if this is a horrible prospect to you, then think and ask questions, and discuss and reason and argue. Inquire, for example, why much less than 1,000th of military budgets is being spent on scientific search for peace, on finding out and reaching for the conditions for a stable and lasting peace. Inquire, for example, how inspection of military computing systems under an international disarmament agreement would be carried out. And more besides. Don't cooperate with horror by your silence. Intensive summer courses. The University of Michigan, Ann Arbor, Michigan, has scheduled a number of intensive summer courses for certain periods in the summer of 1959. Of these 8 relate particularly to the computer field. Automatic Control, June 15 to 24. Introduction to Standard Methods of Numerical Analysis, June 15 to 26. Introduction to Digital Computer Engineering, June 29 to July 10. Advanced Theory of the Logical Design of Digital Computers, June 29 to July 10. Advanced Numerical Analysis, June 29 to July 10. Computer Programming and Artificial Intelligence, June 29 to July 10. Foundations and Tools of Operations Research and the Management Sciences Random Processes, June 29 to July 10. September 7-11. Calendar of Coming Events April 2 to 4, Joint Meeting, Institute of Mathematical Statistics, Central Region, and Association for Computing Machinery, Case Institute of Technology, Cleveland, Ohio. May 11 to 13, Joint Automation Conference, Chicago, Ill. May 14 to 15, 4th Annual Electronic Data Processing Conference, University of Alabama, University, Alabama. May 14 to 15, Operations Research Society of America. National Meeting, Shoreham Hotel, Washington, D.C. June 15 to 20, International Conference on Information Processing, Paris, France. June 22 to 25, British Computer Society First Annual Conference, Cambridge, England. September 1 to 3, Association for Computing Machinery Annual Meeting, Mass. INST of Technology, Cambridge, Mass. Computers and Automation for March, 1959. 3 times. Actual size. Mock-up of Claire type. F relay enlarged to show. Operating mechanism. Note bifurcated contacts, which enable this relay to handle a wide variety of contact loads. With this one relay, you can handle contact loads from 3 amperes. Actual size. All popular mounting arrangements are available. Terminal arrangements nicely suited to 1/10 inch. Grid spacing down to 1 microampere, 1 millivolt. In one relay, the type F Claire provides a precise component of unusual flexibility for long life operation under a wide variety of contact loads. Tests have shown a performance of over 22,500,000 operations at 0.1 ampere, 115 volts AC. Minimum contact life at 3 amperes is 100,000 operations. Contacts have carried 1 microampere, 1 millivolt, for 700,000 operations with a failure resistance of 500 ohms, with no misses recorded. This amazing low-level life is primarily a result of the use of gold-plated contacts. These same contacts, however, will carry up to 3 amperes. A special plug-in mounting arrangement that will stand extreme shock and vibration is now available. The Claire type F relay is hermetically sealed, operates perfectly in a wide range of temperatures, withstands heavy shock and vibration, is fast and more than moderately sensitive. Send for Engineering Bulletin Number 124. Write or call CP Clare & Co., 3101. Pratt Boulevard, Chicago 45, Illinois _in. Canada, CP Clare Canada Limited. 2700 Jane Street, Toronto 15. Cable. Address, Clare La Y. ___, E, R : YL. L. For $T in $THERNDU $TRICI1, Phi I and if. D, H.W. __, equals, W __, dot. WU, dash, 31. T he followin I a compilation of patents pertaining to computers and associated equipment from the Official Gazette of the United States Patent Office, dates of issue. As indicated, each entry consists of patent number / inventor, S, / as, signee / invention. Printed copies of patents may be obtained from the U.S. Commissioner of Patents, Wash. Ington 25, D.C., at a cost of 25 cents each. July 22, 1958, 2,844,308 I. Roger R. Duss. Sign, Paris, Father I. Société d'Électronique. Et d'Automatisme, a corp of Father I. Circuits for the addition and subtraction of numbers. 2,844,310 I. John Robert Cartwright. Letchworth, Eng. I. A data column. Shifting device. 2,844,312 I. James M. McCampbell, San Francisco, California. IUSA as Repra. Adfig. Shift registers. Lowest power per bit, up to 25 stages driven by a 50 MW tran. Sister. Lowest cost per bit, $4.90 for 25 kc unit. Highest 1/0 ratio, up to 30/1 minimum. High reliability from generous operating margins, long life, 3 years of field testing. Complete shift register. Line, magnetic, transistor, coin. Incident current. Among users of our shift regis. TERS, DuPont, Eastman Kodak. IBM, Lockheed Aircraft. Try our sample register as assemblies, ready to operate. See the DIN difference for your self. DIN Controls, Inc. 40 Leon Street, Boston 15, Massachusetts. Telephone, Highlands 5 to 5640. TWX, Roxbury, Massachusetts, 1057. NEAETC, Pi Effet. 2, Dislation Controls Incorporated. 40 Leon Street, Boston 15, Mass. Please send me information on O shift registers, 0 counters. O buffer storage. My name and address are attached. New patents. Raymond R. Skolnick. Reg. Patent Agent. Ford Inst. Co., DIV of Sperry Rand Corp. Long Island City 1, New York. Scented by the seconds of the Navy IA. Radiation Intensity Dosage Analog. Computer. July 29, 1958, 2,845,219 I. Gerard J.R. Peel, Paris, Father I. Société d'Électronique. ELD Automatisme, Paris, Father I. A scale conversion apparatus for converting a numerical quantity expressed in a binary scale of notation to the corresponding expression of said quantity in the denary scale of notation. 2,845,220 I Lowell S. Bensky and Linder. C. Hobbs, Haddonfield, N.J. I Radio. Corporation of America, a corporation of Delaware. I an electronic comparator. 2,845,222 I Joseph F. Jenna and Robert E. Stahlcup, Indianapolis, IND. USA. As represented by the seconds of the Navy. IA high-speed parallel type binary. Electronic adder. 2,845,597 I George D. Perkins, Duarte. California. I Consolidated Electrodynamics Corp., Pasadena, California. IA System 4. Digitizing Analog Signals. 2,845,609 I Edward A. Newman, Ted. Dington, Donald W. Davies, South Sea. And David O. Clayton, Hanwell, Lon. Don, Eng. I National Research Development Corp., London, Eng. IA. Method of recording digital information. 2,845,610 I Warren A. Cornell, Murray Hill, and John H. McGignan, New Providence, NJ, and Orlando J. Moore, PHY, New York, NY. I Bell Telephone Laboratories Incorporated, New York, NY. A magnetic data storage system. 2,845,611 I Frederick C. Williams, Oak Hurst, Romilly, Eng. I National Research Development Corp., London, Eng. IA Digital Storage System. August 5, 1958, 2,846,141 I Roy Bailey, Woolhampton, and Gerhard Liebman. Aldermaston, Eng. I Sunvik Controls Limited, London, Eng. I an Electrical Analog Computing Apparatus. 2,846,593 I Eugene A. Sands, Mount Kiss, Co., NY. IA Logical Computing Element. August 12, 1958, 2,847,161 I Alexander Greenfield, Detroit, Mich. I Bendix Aviation Corp., Detroit, Mich. IA. Counting Circuit. 2,847,568 I Julian A. Salcedo, Covina, California. I Hoffman Electronics Corp., A. Corp of California. IA Distance Digital Display Circuit Arrangement. 2,847,615 I Douglas E. Engelbart, 0AK. Land, California. I Digital Techniques, NC. Berkeley, California. IA Memory Device. 2,847,658 I Francis V. Adams, Endicott, NY. I International Business Machines Corp., New York, NY. IA Drum Storage Lookup Device. August 19, 1958, 2,848,160 I Ben Bider, Man, Cedar Rapids, Iowa. I Collins Radioco, Cedar Rapids, Iowa. IA Trigonometric Computing Apparatus. 2,848,161 I Harry J. Wall, Audubon, N. IRCA, a Corp of Dell. IN. Analog multiplication device. 2,848,532. I. Robert L. Vida, Elmhurst. NY. I. Underwood Corp., New York. NY. IA Data Processor. 2,848,605. I. Saul Kukinski, Phoenixville. PA. I. Burroughs Corp., Detroit, Mich. I. An analog to digital conversion. Using cathode ray sampler to control a cathode ray coder. 2,848,670. I. Leroy U.S. Kelling and Law. Rents R. Peasley, Schenectady, NY. General Electric Co., a corp of New York. I. An automatic programming servomotor control system. 2,848,709. 1. Curtis M. Yansky, New York. And Arthur W. Vodak, Garden City. NY. I. Sperry Rand Corp., a corp of Delaware. IA Digital Data Storage CIR. Quit. August 26, 1958, 2,849,181. I. Jules Let. Man, Trenton, N. IRCA, a corp. of Dell. IA Time Division Computing. Device. 2,849,183. I. John H. Cook, Silver Spring. MD. I. USA as represented by the Seconds. Retiary of the Navy. I. An analyzer for plotting the probability of the occurrence of a given amplitude in an electrical wave. 2,849,184. I. Arden H. Frederick, Mount Kisco, and John W. Gray, Pleasantville, NY. I. General Precision Lab, Inc., a corp of NY. IA Navigational System Wind Computer. 2,849,704. I. Glenn A. Neff, Pasadena, California. I. Consolidated Electrodynamics Corp., Pasadena, California. IA Data Processing System. 2,849,705. I. Monroe K. Haynes, PAL. Keepsy, NY. IBM Corp., New York, NY. IA Multidimensional High Speed Magnetic Element Memory Tricks. 2,849,706. I. Charles L. Hamblin, London. Eng. I. General Electric Co., Lim, Lon. Don, Eng. I. An electronic circuit for deriving a voltage proportional to the logarithms of the magnitude of a variable quantity. September 2, 1958, 2,850,236. I. David H. Schaefer, Washington, D.C., and Donald G. Skorgia, Pittsburgh, PA. I. USA as represented by the Seconds of the Navy. I. A polarity-sensitive analog divider. 2,850,237. I. Gordon C. Irwin, Fairhaven, NJ. Bell Telephone Lab, Inc., New York, NY. IA Number Scanning CIR. Quit. Computers and Automation for March, 1959. In the computer field. Who? What? Where? Answers. Basic source information. Available to you from computers and automation. People. Mailing plates for over 18,500 computer people. We address your envelopes. $19 per m. Organizations. The Computer Directory and Buyers Guide, 1958, the June, 1958, issue of Computers and Automation 740. Organization listings, 3,220. Product and service listings, $6. Glossary of terms and expressions, over 480. Careful, clear, understandable. Definitions. 4th Cumulative Edition. 20 or more copies, 10% discount, $1. Back copies. For 7 years of publication. If available, $1.25 each, except direct. Tory issues June 1955 to 1957, $4. Each, June, 1958, $6. Subscriptions. USA 1 year $5.50, 2 years $10.50. Add 50C per year for Canada, $1 per year elsewhere. Bulk subscriptions. These rates apply to prepaid subscriptions to computers and automation coming in together direct to the publisher. Bulk subscription rates. United States. Number of simultaneous subscriptions, 7 or more. 4 to 6. 3. 2. Rate for each subscription, and resulting saving. 1 year 2 years. $4.20, 24%, $7.25, 31%. 4.60, 16, 8.00, 24. 5.00, 9, 8.80, 16. 5.25, 5, 9.55, 9. For Canada, add 50 cents for each year. Outside of the United States and Canada, add $1 for each year. Send prepaid orders or requests for more information to Computers and Automation. 815 Washington Street, Newtonville 60, Mass. If not satisfactory, returnable in 7 days. For full refund. 2,850,667 / Frederick C. Williams, Rom. Illy, Eng. / National Research Develop. Ment Corp., London, Eng. / an AP. Paratus for storing binary digits. 2,850,719 / Richard J. LaManna, Orange. NJ. / Monroe Calculating Machine. Co. Orange, N. / a data entering means for storage devices. September 9, 1958, 2,851,219 / Luther W. Hussey, Sparta, N. / Bell Telephone Lab, Inc., New York, NY. / a serial adder for adding successive pairs of binary DGTS. 2,851,220 / Richard E. Kimes, Concord, California. / Beckman Instruments Incorporated. South Pasadena, California. / a transistor counting circuit for counting electric pulses. September 16, 1958, 2,852,191 / Howard A. Lazarus, Brooklyn, NY. / Reeves in. Instrument Corp., New York, NY. / a circuit for computing the cosine of the angular position of a shaft. 2,852,764 / Donald Mell. Frothingham, Darien, Con. / Barnes Biniring. Co., Stamford, Con. / a data conver. Zion System. September 23, 1958, 2,853,234 Roger R. Dussin Paris Father Société d'Electron. Et d'Automatisme, Corbevoy, Fr. An electronic digital adder subtractor. Computer device. 2,853,235 John F. Brinster, Homer M. Hill, Jr., and Erwin Donath, Princeton. N. Applied Science Corp. of Prince. Ton, Princeton, N. A binary digit multiplier circuit for use in digital computers. 2,853,238 Robert R. Johnson, Pasadena, California. Hughes Aircraft Co., Culver City, California. A binary coded flip-flop counter. 2,853,357 Alfred W. Barber, Flushing, NY. John T. Potter, Locust Valley, NY. A pulse packing system for magnetic recording of binary coded information. 2,853,697 Sheldon D. Silliman, Forest Hills, and Willard A. Dare, Pittsburgh, PA. Westinghouse Electric Corp., East Pittsburgh, PA. A logic element DESI. Mal register. 2,853,699 Stephen O'Neill, Lexington, Mass. USA as represented by the Seconds of the Air Force / a digital to analog shaft position transducer. September 30, 1958, 2,854,191 Gordon Rice. Beck, Basking Ridge, NJ. Beltella. Phone Lab, Inc., New York, NY. An apparatus for computing the correlation of two signals. 2,854,18 William W. Farris, Rochester, New York / General Dynamics Corp., Rochester, NY. A digit adding selector. 2,854,573 James E. Ferneeks, WAP. Pingers Falls, NY. International Business Machines Corp., New York, NY. An electronic storage device employing a fantastion with a range meant for gating synchronizing pulses. Computers and Automation for March, 1959. Data Processing Engineers. To maximize intercept performance with General Electric. Sample problem, determine the optimum detection criteria for a particular class of radar target. Examine the potentials for basic information in the applicable class of radars. Specify the logi-cal criteria for the design of a data processing system to utilize the chosen class of radar against the particular target. Intercept data to be evaluated increases geometrically with increasing target speeds. As target speeds enter the hypersonic region, necessitating proportionate increases in radar range, a rising hood of target in formation demands split-second evaluation, data link transmise, Zion and conversion into forms. Useful for tactical decision making. Are you interested in the problems of applying non-classical approaches to achieve a new order of systems capabilities critically needed? If so, you are in to look into the many Opportunities open now on a diversity of projects in Asterisk 3D display systems. Asterisk large screen display systems. Asterisk digital detector trackers. Asterisk air traffic control systems. Asterisk integrated air defense. Environments. Positions at several levels. Right to MEOGE. Heavy Military Electronics Department. General Electric. Court Street, Syracuse, New York. 33. Who's Who in the computer field. A full entry in the Who's Who in the computer field consists of name/title, organization, address, /interests, the capital letters of the abbreviations are the initial letters of applications, business, construction, design, electronics, logic, mathematics, programming, sales, / year of birth, college or last school. Background, year of entering the computer field, occupation/other. Information such as distinctions, publications, etc. An absence of information is indicated by -. Other abbreviations are used, which may be easily guessed, like those in the telephone book. Every now and then a group of completed Who's Who entry forms come into us together from a single organization. This is a considerable help to a compiler, and we thank the people who are kind enough to arrange this. In such cases, the organization and the address are represented by 3 dots. Supplement. Following are several sets of such Who's Who entries. Bendix Aviation Corp., Systems Division. 3300 Plymouth Road, Ann Arbor, Michigan. Beecher, William D. /Staffingr. /DL/29, Tri-State Call, V of Mich. 58, Ingr /member of IR. Buzzard, Robert D. /Ingr. /A/ 26, MIT, San Diego State Call, 53. Die, Robert H. /Staffingr. /AL/ 29, V of Mich, 53 /Tau Beta Pi, ETA. Kappa Nu, co-author of VMware Tech. RPT number 79. Gordon, David George /Staffingr. /DL/34, Case INST of Tech, 58, Ingr. Gildner, Gilbert G. /Staffingr. /ADL/32, Mitch Coley of Mining and Tech, 57, Elects Ingr, Dataproc. Johnston, George A. /AD/31. NWNV, 56, Ingr. Collins, Arthur B. /Acetol/29. Mitch State v. 53. Klosterm, N. James L. /Staffingr. /Alp/33, Western Mich v. 55. Luffray, J.R., Bruce /Dataproc Proj. Ingr. /Acetol/29, V. Niv of Con, 52. Potter, William H. /Ingr. /EMDL/ 22, IND VNiv, V of Mich, 52. 5 Me Data Block Datapoc. Versatile, high-speed digital building blocks for data handling, data conversion systems, special purpose counters, process control and automation, lab, oratory research and test equipment, NMR instrumentation, electromagnets and power supplies, error signal comparator, digital components, Harvey. Wells Electronics Incorporated. Research and Development Division. 5168 Washington Street, West Roxbury 32, Mass. Smith, James F. /MP/29, Sue N. Methodist VNiv, 58. Van Valkenburg, ES/Head, Data Proc. and Display Department. /ACDL/23. V of Mitch, 47, Ingr. Computer Control Co., 2251, Berry Avenue. Los Angeles 64, California. Alexander, James C. /Head of Autom. PRGMG. /AMP/30, VNiv of. Wash, 55, Sister PRGMR. Arnold, Dorothy E. /Head, WLA Math. GP. /CDMPS/22, VNiv of. Arizona, 53, Math. Bow, Harold W. /Sister PROJ Ingr. /AELM/24, CIT, 51, Elecningr. Bomber, William E. /Assistant Ingr, CDEL/29, VCLA, 56, Ingr. Brathwaite, Lewis K. /Analyst, /AMP/27, NYV Grad SCH, 54, Math. Brinkerhoff, Frank E. /PRGMR. /AMP/32, VNiv SoCal, 56, Math. Coker, Louise /Math PRGMR. MP/- VCLA, 55, Math. Dyer, James /Analyst. MP/21. VCLA, 52, Math. Fairbrother, Edward M. /PRGMR. MP/29, VCLA, 56, Math. Frieden, Howard /Math PRGMR. LMP/35, VNiv of Chi, 54, Math. Deasy, Gerald J. /PRGMR. /AMP/. 34, Arizona State at Tempe, 6, Math. Holden, Louise /PRGMR. /P/0.5. NWN VNiv, Evanston, Ill, 54, PRGMR. Holguin, Raoul E. /PRGMR. MP/28. VCLA, 53, PRGMR. Camp, Elza M. /PRGMR. MP/. 16, VNiv of Mitch, 54, Math. Kaczynski, Walter J. /Math Sales MGR. /Abdulm/31, VNiv of. Kahn, VCLA, 54, Math. Macmillan, Malcolm C. /Analyst. LMP/27, VCLA, 55, Math. Nichols, Alexander /PRGMR. AMP. /32, VCLA, 54, Math. Rawl, Wilfred E. /Math. MP/. 27, IND VNiv, USC, UCLA, 52, Math. Ritland, Lloyd 0/Head, CCC Math GP. FMP/06, VCLA, 56, PRGMR. Skidmore, John W. /PRGMR. MP. /05, Case INST of Tech, 57, Math. Sparger, Janet L. /Compare Operator. ALMP/27, LAJR Call, 56, Compare Operator. Sprong, DC/Head, Engineering Department. /CDEL/09, VCLA, 48, Ingr. Stockmel, Frank/Head, Math Department. /AMP/21, University of Rochester, 51. Mathen. Wesley, Louis W/Compare Analyst. /MP/20, VNiv of Min, 42, Mathen. Wiegert, Samuel C/PRGMR. /MP/29, Iowa St. Teach Call, 55. Mathen. Remington Rand Univac, DIV of Sperry. Rand Corp, Univac Park, St. Paul 16. Min. Callahan, James I/Prod Planner. 34 Computers and Automation for March, 1959. AB/29, W.M. and Mary, University of Call on Clevides Computer Know-How. Ill, 56, Prod Planner. Clemens, Eric H/MGR, New Products. /ABMP/19, University of Min. 48, Meckengr, Mathen. Kramer, John B/Mathen. /ABP/ 23, University of Colorado, 50, Mathen. Dial, J0/Head, Prod Proposal Seconds. /Planning Computer Products/ New. 25, University of NC, 49, Physicist. Erickson, Gerald L/Mathen. /A/. 31, University of Min, MA, 54, Prod. Planning. Higgins, Jr., Leo J., Applicants Analyst. /ABP/24, University of Wisc, BBA 51. 56 Accountant, prior to computers, Phi Beta Kappa, Beta Gamma Sigma. Hildreth, Dalton L/Applicants Analyst. Low-NOL.SE. /ABP/21, University of Ill, 56, AC. Countant. Halston, Alfred A/Systems Analyst. /AP, Air Traffic Contract System /20. Antec State Coley, 56, Analyst. Jarvis, Donald T/Subver, Systems Re. U, E22NIR. 56. Memory Drum. K, E.T. Avid. E/Subver, New Prod Department. /ABD/23, University of VA, 49, Prod. Planning. Lunger, George F/Staff Consultant. /Abdelm/18, University of Mich, 56. Mathelstatin/Theory of Queens PUBL. D. By Univac DIV, co-author of 2 papers. Rive on Lake Trout Fisheries. Renacker, Harvey E/MGR, Planning. Support Department. /Prod Planning of. New Prod and Modifications to Current Prod. UX/23, U.S. Naval Academic, 54, Elecl. Ingr. Sampson, Louis H/Applicants Analyst. /Abdelm/27, University of Min. 56, Applicants Analyst. The Datix Corporation, 6000 Camp. Bowie Boulevard, Fort Worth, Texas. Austin, Kenneth L/Press. /Abdel. MPS/25, University of Oklahoma, 50, MGT of. Compare SVCORGN. Ergel, John L/Datatician. /A/. 29, Georgia Tech, 55, Cherningr. Murata, Anthony F/dir of Data PROC. SVCs. /ABMP/30, Texas Chris. Tien University, 56, DIR, Data PROC SVC/ Journal of Petroleum Technology, Oil and Gas Journal, 9th Oil Recovery Conference at Texas A&M. McIntyre, Robert L/Vice Pres. AP/24, Purdue and Iowa State, 50. Registered Ingres/20, Patents in Field of Engineering and Papers in Tech Journals. Medvedev, Marian C/Datatician. /APS, Engineering/29, Lamar State Call. Of Tech, 56, Campere PRGMR. Roberts, Cloyd M/CH Avons. /A/27, Texas A&M, 56, CH Avons. Schneider, John C/Datatician. MPS, Engineering, Stat Analysis/28, ST. Edwards University, 53, Data PROC Ingr. TID, Mrs. Laveda/Statistician. M, Statistics, Engineering/06, University of Chic and Universal of MD, 53, Mathelstatten. Vinson, John A/Datatician. /AMPS. Engineering Prob/29, Centenary Colley of Law. 55, Mathn. This stainless steel belt drive was developed to reduce the noise of instantaneous speed variations and backlash inherent in gear drives. In actual tests with FM recorded data, the noise level was 4 to 6 decibels lower than the finest gear drives available for comparison. Signal-to-noise ratios of over 60 dB, with noise cancellation, have been measured. Unusually durable, this stainless steel belt drive holds its low noise level for years. While this drive is for a special purpose magnetic memory drum, similar drives can be designed for any memory drum or tape transport. Other divisions of Clevite Corporation. Serving industry and defense. Brush Instruments Cleveland Graphite. Bronze Clevite Electronic Components. Clevite Harris Products Clevite Limited. Clevite Ordnance Clevite Research Sen. Clevite Transistor Products Inter. Meta 2 GmbH. Computers and Automation for March, 1959. This precision component is just one example of the specialized engineering and production skills to be found at Clevite, Texas Division. We are producing complete analog computer systems with an overall accuracy of 1 part in 6,000. We are also equipped to design and build subsystems and computer-controlled servo systems to any specification. If you want to know more about us and what we can do, just write. We will be glad to send you our brochure describing facilities or arrange for an appointment at your convenience. Clevite Corporation, Texas DV. Zion, 9820 South Main Street. Houston 25, Texas. Clevite Corporation. TEXAS Division. 35. Computer Specialists. Grow professionally. With Burroughs. 36. Burroughs Corporation. Electrodata Division, has just completed the most successful sales year in its 5-year history. In this dynamic, youthful organization, New opportunities are constantly arising for professionals who seek the advantages of a completely computer-centered company. In all its aspects, Electrodata division has much to offer. Openings exist in Pasadena in product planning, applied programming, publications and training, and in scientific and commercial applications. In the field, throughout the U.S., there are openings for application and programming specialists who are interested in being part of a sales operation, with all its variety, excitement, and rewards. If you feel you can meet the standards of this quality-conscious organization, and if you want to participate personally in one of the most stimulating business dramas of the 20th century, contact the nearest Burroughs Electrodata office or write to Professional Personnel Director in Pasadena, Burroughs Corporation, Electrodata Division, PASAD ENACAL if 0 RNIA, New DLTFENSIONS, in Electronic J and Dala PROO Jing, YJDMS, General Electric Company, Evandale, Computations Building 305, Cincinnati, 15, Ohio. Allison, MH/MGR, Automatic Test Data. Proc Unit /P/26, Ohio State. UN4, 57. Bailey, Barbara Wells /Numerical UN. A list. ILPI 32, Goucher COL. Leg, BA Physics, 54, PRGMR. Baker, JM/Automatic Test Data Red. Analyst /P, Testing Area of Data. Reduction /26, Hanover Colleague. 55. Banan, Frederick B/MGR, Compare Tech. Neeks Dev /P Opernel Systems /14, Worcester Poly INST, 56. Bartlett, Jan C/Systems Dev Analyst. LMP, Systems/32, University of CIN. Senate, 56, 704 Systems Dev. Boer, WL/Numerical Analyst. /ALMP/28, Purdue University, 58. Campbell, Donald J/Math Compton. A list. /LMP/33, University of Mich. 56, PRGMR. Kaplan, LN/Bus Systems Analyst. /Ablum/3D, Carnegie Tech, 55. Bus Systems Analyst /ORGN of Sci. Entificum Installations in Computers and Automation. Carr, George J/MGR, Thermodynamics and Performance Comps. /AMP/. 32, Villa Madonna Coley, University of CIN. Senate, 55, Math. Clarks, Dorothea S/Automatic Coding. Analyst /Systems and Automatic Coding Dev I-21, Hiram College. 53. Cruikshank, Robert D/Statl Analyst /AM/31, Oberlin College. 57, Math, Staten. Donovan, David P/MGR Comptons Fa. Seeley Ties /BP/24, University of CIN. Senate. Erner, Georgie /Thermodynamics. Comptons Analyst /LMP/3. Miami University, Oxford, Ohio, 58, /Ma Thesis on Applications of the Fields of Integers, modulo P, to the Fermat problem. Ensminger, Thomas A. /Thermodynamics. Compt's analyst. /LMP/26. VA State Coley 57. Erickson, Dorith Y/PRGMR. /AMP. /36, Colorado Coley, 56, PRGMR. Hahn, Donald J. /Thermodynamic Com. PN Specialist. AMP/31, University of Cincinnati, 54. Holt, Roy Vincent /Engineering Systems Com. PN's Analyst. /AM/26, Ohio State University, 52, Math I Analyst. Hunter, William Heber /Automatic Test. Dataproc Analyst. /ALMP. /35, Ohio UN4, 58. Kuzarian, James H /Automatic Test Data. Proc Analyst. /AP, Test and Tech Data Proc /33, Wayne State University, 57. Marlette, Laura Lee /PRGMR. /AMP. /32, Hanover Coley, Xavier University, 58. PRGMR. Robertson, Yancey V /PRGMR. /AMP/34, Georgetown Coley, 55. PRGMR. Schatz, Vernon L /MGR, Bus Systems. Uplans. /UP/21, Iowa State. Coley, 57. Engineering /registered in GRU, Ohio. Member SAE. Schneider, Martha May /Numerical A list. /MP/34, University of KY, 56. Numerical Analyst. Who's who in the computer field. Each year we like to bring up to date our who's who in the computer field. We are currently asking all computer people to fill in the following who's who entry form and send it to us for their free listing in the who's who that we publish from time to time in Computers and Automation. We are often asked questions about computer people, and if we have up-to-date information in our file, we can answer those questions. If you are interested in the computer field, please fill in and send us the following who's who entry form. To avoid tearing the magazine, the form may be copied on any piece of paper. Name. Please print your address, your organization, its address, your title, your main computer interests, applications, business, construction, design, electronics, logic, mathematics, programming, sales, other, specify, year of birth, college or last school, underscore, year entered the computer field, occupation, underscore, anything else, publications, distinct ions, etc., dash, dash. When you have filled in this entry form, please send it to who's who editor, Computers and Automation, 815 Washington Street, Newtonville, 60, Mass. Computers and Automation for March, 1959. Manuscripts. We are interested in articles, papers, reference information, and discussion relating to computers and automation. To be considered for any particular issue, the manuscript, should be in our hands by the 1st of the preceding month. Articles, we desire to publish articles that are factual, useful, understandable, and interesting to many kinds of people engaged in one part or another of the field of computers and automation. In this audience are many people who have expert knowledge of some part of the field, but who are laymen in other parts of it. Consequently, a writer should seek to explain his subject, and show its context and significance. He should define your familiar terms, or use them in a way that makes their meaning unmistakable. He should identify unfamiliar persons with a few words. He should use examples, details, comparisons, analogies, etc., whenever they may help readers to understand a difficult point. He should give data supporting his argument and evidence for his assertions. We look particularly for articles that explore ideas in the field of computers and automation, and their applications and implications. An article may certainly be controversial if the subject is discussed reasonably. Ordinarily, the length should be 1,000 to 3,000 words. A suggestion for an article should be submitted to us before too much work is done. Technical papers, many of the foregoing requirements for articles do not necessarily apply to technical papers. Undefined technical terms, unfamiliar assumptions, mathematics, circuit diagrams, etc., may be entirely appropriate. Topics interesting probably to only a few people are acceptable. Reference information, we desire to print or reprint reference information, lists, rosters, abstracts, bibliographies, etc., of use to computer people. We are interested in making arrangements for systematic publication from time to time of such information with other people besides our own staff. Anyone who would like to take the responsibility for a type of reference information should write us. News and discussion, we desire to print news, brief discussions, arguments, and announcements, letters, etc., anything, in fact. If it is not advertising and is likely to be of substantial interest to computer people. Payments, in many cases, we make small token payments for articles and papers, if the author wishes to be paid. The rate is ordinarily YZC a word, the maximum is $15. And both depend on length in words. Whether printed before, whether article or paper, etc. All suggestions, manuscripts, and inquiries about editorial material should be addressed to the editor, Computers and Automation, 815 Washington Street, Newtonville 60, Mass. Stevens, Garnett L/Mathel Compton. A list. /ALMP/31, University of KY, 56, Math. Toth, Fred C/PRGMR. /Ablum/ 34, University of Cincinnati, 57. Trenkamp, Paul J/Engine Performance. Compton's Analyst. /LMP/3. Villa Madonna College, 55. Tumbas, James J/Specialist, Statl. Uplands. /AM/29, University of Dayton, Purdue University, 56, Staten. Vollenwaiter, Mrs. Deborah B. /Reactor. Competence Analyst. /LMP /33. Wellesley Coley, University of Cincinnati. 55. Watson, Dunnelly H. Mechanics Competence Analyst. /AMP, Astronomy /29. Omaha University, Indiana University, University of Cincinnati, 55, Math Analyst /CIN. Cincinnati Engineering Society, many pubs on PRGMG, etc. Watson, Flora J. Part-time Compare. PRGMR. /MP, Astronomy /28. Hunter College Indiana University, 50, and Ulysses PRGMG /Sigma 11. Williams, Gregory P. Compare Applicants. Specialist. /AMP, Stat /26, Co. Lumbia Coley, 54. Woldstad, Carol Numerical Analyst. /P 34, University of Mich, 57, Math. U.S. Navy, Electronic Supply Office. Building 3500, Great Lakes, Ill. Adams, Alexander Program Branch. Head. /Po 21, Newark Coley. University of Allah, 56, Compare PRGMG. Alexander, Clarence 0 /Sub Compare. PRGMR. /Ablupo 27, Met SCH. Of Music, 56, SYST Analyst, PRGMG. Clark, Betty J /Compare PRGMR. /P 24, Ohio State University, Wilberforce. University, 57, PRGMR. Copeland, James L /Compare PRGMR. /LP 32, Lake Forest Coley, 56. PRGMR. Hayes, Lucy A /Compare PRGMR. /P 24, University of Wyo, 56, PRGMR. Johnson, June M /Compare PRGMR. /27, Wright J.R. Coley, 56, PRGMR. Keddy, Clifford M /Ablooms. /25, Western Mich University, 56, PRGMR. Analyst. Coleman, Robert C /Compare PRGMR. /ACTELP 24, 57, PRGMR. Cula, Walter A /Compare PRGMR. ALP 26, 57, PRGMR. Lesko, Nick J /Supervisory Compare. PRGMR. /ABLP 28, Lane Tech. 56, PRGMR. Lillehammer, Arn M, Jr., /Compare PRGMR. /Ablum 29, Wisk State Teach. Ers Coley, 57, PRGMR. Matashek, Edith /Compare PRGMR, INTE. Graded Data Proc DIV. /BP 22, University of Chi, 55, PRGMR. Neiman, Clifford R /Assistant DIR, INTE. Graded Data PROC DIV. /OB 18. University of Chicago, 55, Systems Dev. Analyst. Ulmer, Jane /Staff Math. /BMP. /12, Wellesley Coley, Sorbonne, École. Libre de Sciences Politiques, Wash. University, 56, Mathn, Residential PRGMR/Phi. Beta Kappa, Sigma Xi, Pi Mu Epsilon. Paul, John William / Compare PRGMR /GMP /26, Cath Universal of Amer. 56, Economist, PRGMR. Computers and Automation for March, 1959. Send us your entrants and your advertising orders for the computer directory. N. Buyer's Guide. 1959. 5th Annual Issue. The only directory in the computer field. The June 1959 issue of Computers and Automation. Contents. Part 1, Roster of Organizations. Each entry gives name of your organization /ad. Dre /telephone number /types of computers, data processors, ACHs, SORIs, components, services, etc., that you produce or offer /approximate number of your employees /year your organization was established. The 1958 directory had over 740 organization entries. Part 2, Buyer's Guide. Roster of products and services. Each expanded bold face entry gives name or identification of product or service /brief description, 22. 50 words, /uses /price range, between, and /heading, under which it should be listed. The 1958 directory had over 3,200 product and service entries in total. The 1959 computer directory will close for entries April 15 and for advertising May 10. Ordinary entries are condensed and are free. Bold face, expanded entries cost $10 each. Except that if you take display advertising, 1 page black and white, $330, 1/6 page, $80, you receive a certain number of expanded boldface entries free. Mail this coupon or a copy of it. 2. Directory Editor. Computers and Automation. 815 Washington Street R140. Newtonville 60, Mass. We enclose our entries for the 1959 computer directory. Please send us more information about the 1959 computer directory. Name, title, organization, address. 37. Battelle Memorial Institute, 505 King Ave, Columbus 1, Ohio. Belzer, Jack /consultant /ablump /10, Cooper Union, 40, Ingramathan /Publoons, many articles on computer applications, including astronomy, thermodynamics, mathematics, engineering, also various tables in book form. Boyd, Roger S. /prime physicist /al, nuclear reactor simulation /31. Ohio State University, 56, physicist /Lee. Sense to operate Battelle Research Reactor. Fletcher, BL /prime physicist AP /22, Ohio State UN4, 56, Fissy. Sist. Gordon, Ben /PROJ leader /aid. Pertaining to analog compare /26, Ohio State University, 55, elect. Ingr. Hulbert Lewis E /prime mathen /MPI 24, Ohio State UN4, 52, Math. Jenkinson, George H/PROJ leader. /Adele/21, Marshall Coley, 47, Ingr. /Pabloon communicating with computers. King, Roland D/PROJ leader. /CDEL/29, Otterbein Coyle, 54, PROJ. Leader in Systems Engineering. Kuhn, George R/Prine Math. /AMP/32, Ohio State University, St. Louis. University, 56, Math. Neely, Thomas R/Prine Math. /AMP/25, Ohio State University, 55. Math. Pritchker, A. Allen B. /PROJ leader. /ABLM/33, Columbia University, Ohio State University, 55, Ingr, both elect and Induslo Pabloons, evaluation of micro film as a method of book storage. Simulation to obtain a system's MES. Of an air dual environment. Smith, Richard L/Prine Ingr. ALMP/33, Ohio State University, 52. Indus Ingr. Solomon, Joseph G/Prine Math. ALMP/31, Ohio State University, 56. Math physicist. Weisberg, Alfred/Prine Math. M/28, University of NH, 57, Math. Weatherby, John K/DIV Chief. ACD/26, Ohio State University, 50, elect. Ingr. Positions are open for computer engineers capable of making significant contributions to advanced computer technology. These positions are in our new research center at Newport Beach, California, overlooking the harbor and the Pacific Ocean, an ideal place to live. These are career opportunities for qualified engineers in an intellectual environment as stimulating as the physical surroundings are ideal. Qualified applicants are invited to send resumes, or inquiries, to Mr. L.R. Staple. Aeronotronic Systems Incorporated, Box NE 486, Newport Beach, California. Telephone Kimberly 5 to 9421. Positions open, areas of interest. Systems engineers, computer and data processors. Logical designers, memory systems. Magnetic memory, flight data entry. Engineers, digital circuit design. Communications, advanced high speed. Engineers, computer systems. Digital computer storage units. Programmers, display devices. Circuit engineers, computer components. Mechanical engineers, solid state devices. Aeronotronic. Advertising in DEX. Following is the index of advertisements. Each item contains name and address of the advertiser / page number where the advertisement appears / name of agency if any. Aeronotronic Systems Incorporated, a subsidiary of Ford Motor Co., 1234 Airway, Glendale, California. Page 38 / Honig Cooper, Harrington and Minor. Bendix Aviation Corp., Computer DIV, 5630 Arbor. Vidi St., Los Angeles, California. Page 17 / Shahad. Vertising Inc. C.P. Clare & Co., 3101 Pratt Boulevard, Chicago 45, Ill. Page 31 / Reinc., Meyer and Finn. Clevite Corp., 9820 South Main Street, Houston 25, Tex. /page 35/Rives, Dyke & Co. DN Controls, 40, Leon Street, Boston 15, Mass. /page 32/ Electrodata DIV of Burroughs Corp., 460 Sierra Madre, Villa, Pasadena, California. /pages 28, 36/ Carson Rob, Ertz Inc. ESC Corp., 534, Bergen Boulevard, Palisades Park, New Jersey. /page 5/ Keys, Martin & Co. General Electric Co., Aircraft Nuclear Propulsion Department. P.O. Box 132, Cincinnati 15, Ohio. /page 39/ Deutsch & Shea Incorporated. General Electric Co., Apparatus Sales Office, Skinnock, Tatey, NY. /page 27/ Bassford Co. 38. General Electric Co., Heavy Military Electronics Department. Court St., Syracuse, NY. /page 33/ Deutsch & Shea Incorporated. Harvey Wells Electronics Incorporated, Research and Develop. Ment DIV, 5168 Washington Street, W. Roxbury 32. Mass. /page 34/ Industrial Marketing Associates. Lockheed Missiles and Space DIV, 962 W. El Camino. Real, Sunnyvale, California. /page 30/ Hal Stebbins Inc. Minneapolis, Honeywell Regulator Co., DATM-ATIC. DIV, Newton Highlands, Mass. /pages 21 to 24/ Batten, Barton, Durstine and Osborne. Philco Corp., Government and Industrial DIV, 4700 WIS. Sahikan Abe, Philadelphia 44, PA. /page 3/ Max. Well Associates Incorporated. Radio Corp of America, Semiconductor and Materials. DIV, Harrison, NJ. /page 40/ Al Paul Lefton Co. Royal McBee Corp., Data Processing DIV, Port Chester, NY. /page 8/ CJ LaRoche & Co. System Development Corp., 2500 Colorado Avenue, Santa Monica, California. /page 7/ Stromberger, Lavine, Mackenzie. Technical Operations, Inc., Burlington, Mass. /page 2/ Dawson McLeod and Stivers. Computers and Automation for March, 1959. Mathematicians, physicists, engineers, me. The complexity of the mathematical problems involved in the design of a reactor for aircraft nuclear propulsion at General Electric has led mathematicians to develop new techniques in the statistical design of experiments, of interest to both applied scientists and theoreticians. At this time a number of positions are open, with groups working on these problems. Apply advanced mathematical procedures and approaches in resolving diverse and complex problems in areas of aircraft nuclear power plant design and development. Requires experience in utilization and capability of high-speed computers. PhD, JWS. Conduct theoretical investigation of the effect of neutrons and photons on matter. PhD. Carry out engineering analysis of physical systems in electromechanical areas, deriving equations associated with system study I developing generalized digital programs for parametric study. PhD, JWS. Analyze and simulate nuclear power plant control systems, through the use of analog computers. Develop control systems integration. JWS, BS. Also, EE with 1 year's experience, to assume operating responsibility for data reduction equipment. Develop data reduction techniques. Formulate engineering analysis computer programs. Mathematicians, engineers, and scientists who value the opportunity to do original work with a company that fosters free inquiry and initiative, are invited to inquire about positions now open in the above areas. Please include salary requirements. With resume. Write to Mr. P.W. Christos, Div 21 MC. Aircraft Nuclear Propulsion Department. General Electric. P.O. Box 132 Cincinnati 15, Ohio. Computers and Automation for March, 1959-39. Kanban D-Width Product, UC. 5075. Curves illustrate typical delay time per stage versus gain bandwidth product and fan out for the switching circuit shown below. Plus 0 vol TS. Note: ALL resista NCE. Value: SA re in OHMS. S vol T-Zener diode. Minimum gain. Band YDTH. Product MC. Minimum. Collector. Breakdown. Volts. Minim UM. DC current. TRA-NSFR. RAT-IO. Maximum. Collector. Capacitance. LJ.1F. 2N643 2N644. 2040. 3030. 2020. 60. 30. Co-LL ector volts ==-7, collector Ma ==-5. Collector current ==-100 La. RCA2N643, RCA2N644, and RCA2N645 FA2 RE Conti roll ED. Minimum gain bandwidth THPRODUCTS, OF20, 40, and 60 MC. RCA continues to pioneer superior quality semiconductor devices with THE. New RCA2N643, RCA2N644, and RCA2N645 drift transistors. THSA3. New units feature Contro LL minimum gain bandwidth products PE remitting. The DESIGN of extremely high-speed non-saturating switching circuits with rise, fall, and propagation time in the order of 20 millimicroseconds. For your high-speed switching circuits RE querying pulse repetition rates up to 10 MC, investigate the superior design possibilities and benefits available to you with the new RCA drift transistors RCA2N643, RCA-ZN644, and RCA2N645 hermetically sealed in cases utilizing dimensions of JETEC to 9. Outline. Your RCA field representative has complete details. Call him today. For technical data, write RCA Commercial Engineering, Section C90NN. Somerville, N. J. Radio Corporation of America. Semiconductor and Materials Division. Somerville, NJ. RCA Field Offices. East, 744, Broad Street. Newark 2, NJ. Humboldt 53900. Northeast, 64 A Street T. Needham Hig HTS 94, Mass. Hill C Re ST 4 to 7200. East Central, 714 New CE Enter Building, Detroit 2, Mich. Trini TY 5 to 5600. Centra AL, Suite 1154, Merchandise MART Plaza. Chicago 54, 3. W Hatiha LL 4 to 2900. West, 6355 was Hinton B Lvd. Los Angeles 22, CA Live. Ramo ND 3 to 8361. Gov. 224 N Wilkie N Sun Street. Dato N, Ohio. Baldwin 6 to 2366. 1625 K Street, NW. We SHI England, DC. DI Strict 71260. Available, 2, at your local authorized RCA distributor.